There is a galaxy that shouldn't be there in Serpens, which is about 600 million light-years away. Hoag's object is a nearly perfect ring of stars circling a spheroidal core that doesn't seem to be affected. There is a nearly empty space between them. The way it moves, its shared redshift, and its dark matter ring all point to a single system. But its shape suggests a catastrophic collision, since it doesn't have any of the expected tidal debris, bars, or warps. The H1 superring, the differences in age and metal content between the core and the ring, and the new high-resolution images have all made the situation worse. It's possible for our models to make ring galaxies, but not this one. The object that shouldn't exist. Astronomers don't even bother to make a big deal out of Hoag's object's location in the sky. It's in Serpens Caput, a quiet, unflashy area of space that doesn't usually have strange things happening in it. Still, 600 million light-years away, we can find one of the most theoretically impossible galaxies ever found. A bright, blue, hot, and aggressively young stellar ring, wrapped around an old red spheroidal core that looks like someone polished a fossil to museum quality. And between them, a nearly empty ring-shaped space that is so dark that even long exposures only show a faint hint of stars. It's like the universe drew two circles on a compass and then told astrophysicists to explain the joke. To even describe Hoag's object properly, you have to pause and reformat your mental template for galaxies. Spiral galaxies flaunt arms, bars, bulges, dust lanes. Ellipticals smudge out like massive star-packed clouds. Irregulars look like cosmic accidents that refuse to be symmetrical. Ring galaxies exist, sure, but they carry scars, distorted cores, visible collisions, warps, spokes, tidal debris. Nothing about Hoag's object matches any of that. It feels engineered, intentional. Clean in a way natural processes rarely achieve. The first strange thing is that the ring and the core have the same redshift. It's not two galaxies stacked on top of each other. They should be together. They move with a steady field of speed. They both live in the same ring of dark matter. However, they act and change like two different life stories that are stuck in the same place. The core is very old and is made up of a group of low-mass stars that are common in circular remains. It's still young and shaky, with big, hot blue stars forming in a very tight band, as if star formation stopped liking every direction but outward. That empty gap between them is the kind of observational data that forces theorists to delete half their notes. In most ring systems, you see spirals or bars connecting the ring to the center, or at least some intermediate star formation that blurs the border. Hoag's gap is as if someone carved out the middle with a gravitational scalpel. A dynamically stable ring should leak stars inward over time or disperse outward. Yet this one hasn't. The boundaries stay crisp, the structure stays locked, and it's not sitting in an active environment either. If Hoag's object lived inside a galaxy cluster, you could blame interactions, RAM pressure stripping, harassment, or some violent tidal influence. But no, its neighborhood is chill. No obvious intruder galaxy. No tidal streams. No shredded stellar debris. The usual suspects in a ring galaxy crime scene are missing. The ring itself is composed of massive, short-lived stars, which means it formed recently on cosmic timescales. The core, meanwhile, is billions of years older. That massive age gap suggests something dramatic happened to funnel gas outward into a ring not too long ago. Problem? We can't find the culprit. The collision hypothesis requires a bullet galaxy punching straight through the center, triggering density waves that sweep gas outward. But Hoag's core is too undisturbed. It's round, smooth. Collision remnants should leave asymmetries, bars, elongations, or at least some rotational kinematic fingerprints. Spectra shows nothing that matches that script. Furthermore, radio telescopes show a wider circle of neutral hydrogen, called an H1 superring, that is much bigger than the bright visual ring. In a way that normal disk galaxies can't do, this shows that Hoag's object has been gathering or holding on to gas. If this system came from a spiral galaxy whose bar broke apart over time, the core should look more like a disk with some rotating structure still there, It is almost exactly spheroidal instead, like a small ellipse that got lost in the wrong neighborhood. Simulations have trouble. Modern hydrodynamic models with better resolution, physics, and feedback factors still can't easily make a ring that is perfectly separated, symmetric, long-lasting, and has a round core that doesn't show any signs of major damage. Either you get garbage, imbalance, cores that aren't stable, or rings that aren't stable. Astrophysicists try to plug in Hoag's object, but it acts like a solution that doesn't meet any of the starting conditions. The blue ring paradox. The strange thing goes from being unusual to what algorithm even made this, around the outside of Hoag's object. In most galaxies, star creation happens in bands or along arms that follow places where gas clouds fall apart because of gravity. That's not what Hoag's ring does. Instead, star formation is limited to a very small circle band. It's almost as if the galaxy drew a line around where stars can form and then maintained it, like a cosmic border patrol. The stars in this ring are bright, young, and overwhelmingly massive. That alone implies a starburst event, one triggered by a large-scale reorganization of gas. But here's the contradiction. The ring is uniform. Not clumpy, not chaotic. Starburst rings in other galaxies tend to be patchy, filled with knots where local gas densities surge. Hoag's ring looks smooth, evenly distributed, photometrically balanced across its entire circumference. You don't get that kind of consistency without a clean, symmetric triggering mechanism, and none of the usual mechanisms survive scrutiny. Collision. A head-on impact can create a density wave that sweeps gas outward into a ring. That's literally how the Cartwheel Galaxy formed. But if Hoag's ring were collision-born, we'd expect clear structural violence. Spokes, tidal tails, a disturbed core. Hoag's core shows none of that. Its velocity dispersion is too calm. Its shape is too round. It rotates like it hasn't been punched in the face by a passing galaxy. Resonance of bars. Galaxies that are spiral and have bars often form rings when their rotations line up at resonance points. However, Hoag's object does not have a bar, or arms that twirl, or even the faint marks of a bar that broke apart billions of years ago. Its center is so round that if it ever had a bar, it would have disappeared so quickly that it has lost even the ability to turn. In theory, gas could come in from strands, settle into a ring, and start the process of star creation. But once more, balance. Accretion doesn't usually make math this good. And if the gas came from outside, its metallicity and motion should be more clear signs that it did. Instead, the ring only partly disagrees with the core, which makes the story less clear instead of more clear. Here's where things really break in terms of tension. The ring's width is very small compared to its diameter. That points to a very small range of orbital radii, where gas had the right density to start forming stars. That is, something pushed or pulled gas into a very thin rotating band and then squeezed it in a way that we don't usually see in the way galaxies move. Then we confront the rotation problem. Kinematic studies show that the ring rotates cohesively with the core's gravitational potential. The whole system behaves as one object, not a merger. But the rotational speeds along the ring indicate a disk-like behavior, even though Hoag's object doesn't appear to have a disk. This is the disk that isn't a disk paradox. The ring acts like the outer edge of a disk galaxy that forgot to form the rest of the disk. The gap absolutely should contain intermediate age stars if this were a fading bar, a dissolving spiral, or a post-collision relaxation zone. But observations show the region is ghostly, faint, almost sterile. Only a handful of ultra-faint clusters show up. That suggests either gas was neatly swept outward, or it never existed between core and ring in the first place. When you look at the mass distribution, one of the most convincing ways to explain the ring, slow secular evolution mixed with long-term gravity resonance, falls apart. The gravity potential has to be tuned almost perfectly for a resonance ring to stay this stable. In other words, too well. Nature can make tuned systems, but not ones that are so perfect that they don't leave any traces. Additionally, the past of star formation in the ring suggests that it is not very old. It's a lot younger than the core, only a few billion years old. That age difference calls for something to happen. But the event must not have been very damaging for the core to have stayed perfect. The dark gap that shouldn't be possible. The ring of Hoag's object is the loud mystery. The dark gap between the ring and the core is the quiet mystery. This is the one that bothers astrophysicists the most because it's hard to explain in any way that makes sense. In almost all scenarios of galaxy formation, there is no natural way to make a circle of almost empty space with a stable radius that doesn't either fill up with stars over time or cause chaos that throws off the balance. Hoag's gap is like the negative picture of a building we think exists but doesn't, or a story part we can see but not read. Start with what the gap actually is. Observations show an annular region where starlight sharply drops off, far more than would be expected from a normal radial brightness gradient. The gap contains almost no intermediate age stellar population, no remnant dust lanes, no dense gas clouds, and only a faint scattering of ultra-low luminosity star clusters. Spectroscopic surveys confirm the absence of significant H-alpha emission or prominent signatures of recent star formation. The region looks dynamically evacuated, as though some gravitational event swept material outward and then sealed the boundary. The gap contradicts the behavior of nearly every known galactic evolution model. If Hoag's object were the product of a head-on collision, you'd expect the density wave to push gas outward, yes. But you'd also expect turbulence, residual clumps, leftover debris streams, and a gradual infill of stellar material over billions of years. The dark annulus shows no such migration. Instead, the boundary between gap and ring is defined almost like a phase transition. Low density on one side, high density on the other, sustained over timescales long enough for stars to form, age, and disperse. One possible theory is that the gap shows the area of greatest evacuation after a density wave. Basically, the area where an event happened in the past and was swept away. But numerical models of ring galaxies always show wider gradients instead of centers that are so sharply cut. There are still sub-rings, spokes, persistent dust, and leftover star populations in the inner structures of the famous Cartwheel galaxy. There is none of this in Hoag's object. It's too clean. Let's consider secular evolution. In a barred spiral galaxy, resonances can clear out certain radii, creating rings and partial gaps. But again, Hoag's object lacks any evidence of a bar, no residual elongation in the core, no bar-like kinematic signatures, no leftover dust that would record the bar's former presence. The core is too round, with velocity dispersion consistent with an early type spheroid, not a disk that once hosted a bar. A resonance gap without a bar is like a whirlpool without rotation. Another attempt invokes a massive past inflow or outflow of gas. For instance, gas could have collapsed inward or been ejected outward by feedback processes. But Hoag's object shows no indication of a central starburst powerful enough to blow out material, nor does it show signs of an active galactic nucleus that could have driven a feedback-induced cavity. There is no ionized gas left over, no high-velocity outflows, no shock signatures. The gap does not look blown out, it looks unoccupied. Kinematics deepen the paradox. The rotational velocities of the ring and inner core reveal a gravitational potential that should allow stars to drift gradually through the gap as they respond to dynamical friction and long-term orbital mixing. Yet they haven't. The gap remains stable enough that its structure hasn't blurred or collapsed over billions of years. That implies either A, extremely fine-tuned mass distribution, or B, some past event placed material into an orbital configuration that resists migration. Neither option is common in galaxy evolution. This is where the pictures of neutral hydrogen, H1, come in. Radio observations show that there is a big, faint H1 envelope around the visual ring. That hydrogen is not spread out evenly. Instead, its structure points to a huge, stretched-out disk that either existed before or still does, though in a highly changed form. Even so, This doesn't help explain the gap because the H1 density drops in the same area as the visual gap. That shows the gap is a real mass minimum and not just a trait of stopping stars from forming. Some researchers say the gap might be the relic signature of a disk that has since disappeared. But this theory runs into the same problem. Disks that have disappeared leave behind signs. They no longer have rotating memory. They leave behind uneven marks in the spread of stars. They leave behind changes in chemicals. There are no signs that Hoag's core used to have a rotating star disk big enough to make a resonance zone. It has a smooth, old population. If the gap were carved early in the galaxy's life, the system would have had billions of years to redistribute material naturally. Yet the contrast remains sharp enough to suggest minimal mixing. This suggests an event more recent than the core's formation, but older than the current ring. That narrows the window. But it also creates contradictions with every inferred timescale. And yet the next layer, the ancient core, might be the biggest contradiction of all. The fossil core with no origin story. On paper, Hoag's object center core is the simplest part of the galaxy. It has an old population of spheroidal stars with no dust, no new stars, and no rotating substructure strong enough to look like a disk. But when looked at in this way, the core becomes one of the most puzzling parts of the whole astronomical system. Any possible history of how a ring galaxy formed can't explain why it is so round, not bothered, and perfectly centered inside the ring. The stellar population tells the first part of the story. Spectra shows an evolved, low-mass, metal-rich mix of stars characteristic of a relaxed, elliptical-like system. That implies the core formed early, likely through rapid star formation and subsequent quenching, standard behavior for many galaxies in the early universe. But here's the contradiction. If the core is an elliptical remnant, then Hoag's object should show signs that it once possessed a surrounding stellar halo or disk that was stripped, merged, or violently restructured. Instead, the region outside the core is empty until the ring begins. Its roundness is another issue. Perfect spheroids in galaxies are rare because they require a long period of gravitational relaxation or a significant merger. But significant mergers leave evidence: debris streams, asymmetries, shells, or at least kinematic scars. Hoag's core displays none of these. It is too clean to be the product of violent restructuring, so maybe it grew slowly, without a big merger. This means that the core most likely formed from an early disk that slowly got hotter and thicker. The center area, on the other hand, would still show signs of rotation, such as a flattened axis ratio or leftover rotational support. From what we can see, almost none. The forces of the core are more like those of a regular elliptical shape than a changed disk shape. This disconnect becomes bigger when you consider alignment. The ring encircles the core almost perfectly, centered with minimal deviation. If the ring were formed by an off-axis collision, asymmetry would be guaranteed. Even a slight angular mismatch would twist the ring or torque the core. Yet both sit concentrically, like two components of a deliberately built structure. Then we evaluate the core's metallicity. It's higher than the rings, suggesting two different evolutionary histories. But the metallicity gap is not huge, meaning the ring's gas was not fully external in origin, nor fully internal. Some fraction of the ring's gas likely came from the system itself, but not from any disk we can currently detect. The chemistry implies a shared ancestry, but divergent timelines. It's like reading two versions of the same story that don't quote the same paragraphs. What's more unbelievable is how the core reacts with the dark matter ring around it. The gravity potential is smooth and well-behaved, as shown by the rotational graph. That means that the ring and core react to a single mass distribution. There are no signs of recent disturbance, lumpiness from mergers, or changes in the shape of the halo. For a circular core to sit in a ring that looks so strangely symmetrical, the system would have to change very little over billions of years. That doesn't work with any situation that tries to use violence to make the ring. So theorists look for alternatives. Could the core be the remnant of an ancient ring or disk? Possibly. But then the ring we see now would have required a second formation event. That presents a double ring life cycle that simulations rarely support. Could the core have formed inside a pre-existing gas torus? The problem: gas torus structures require precise angular momentum and consistent inflow conditions, which are hard to maintain without environmental shaping. Every idea about the core either doesn't fit with the ring's youth, the gap's emptiness, or the halo's balance. The core is petrified, but it's not arranged in a way that makes sense with the rest of the structure. It should be the one part of the galaxy that makes things clear, but instead, it makes all the contradictions even stronger. The ring core kinematics that break the model. One of the scariest things about Hoag's object is that its movements don't make sense when compared to how it looks. When scientists map the speeds of the gas and stars in the system, they get a moving structure that works like a single galaxy. It's smooth, well organized, and governed by gravity. But when those researchers look at the motions and the anatomy side by side, they find that the whole system is broken up into inconsistencies. Hoag's object moves like it should be a normal disk plus bulge galaxy, but it looks like it should have been violently rearranged or partly rebuilt through catastrophic interaction. The main reason why the galaxy is still a mystery is this conflict between mechanics and morphology. The core and ring share the same systemic velocity and redshift. They are not two overlapping galaxies. They are part of the same gravitational structure, no question, but sharing the same redshift is the easy part. What matters is how they rotate. Velocity maps reveal that both components follow a consistent gravitational potential defined by a smooth dark matter halo. The ring rotates in an orbit that suggests a massive, stable, nearly circular distribution. The core shows velocity dispersion, typical of an elliptical galaxy. Together, they fit the potential well, almost too perfectly. The first paradox is that if Hoag's object formed by impact, which is the most straightforward way to explain a ring, then the impact should have left chaotic kinematic signs like velocity shears, asymmetries, shock fronts, or movements that aren't circular. There are none here. It's amazing how smooth the turning curve is. There are no more high-speed groups left over, no extra friends. There's nothing that looks like the nasty scars that standard collisional rings leave behind. The second paradox: the ring rotates like the outer edge of a disk, but Hoag's object has no disk. Disk galaxies show rotational support, flattened shapes, measurable axis ratios, and stellar orbits aligned in a plane. Hoag's core is not flattened. It is not rotationally supported. It behaves like a pressure-supported spheroid, the kind you expect in an elliptical or a bulge. In a normal galaxy, you do not get a perfectly circular, massive, star-forming ring without a disk to guide it. Rings require angular momentum continuity. Hoag's ring has continuity, but no host disk to inherit it from. Then comes the issue of orbit coupling. For the ring to remain locked in such an extremely thin radial range, it must inhabit a remarkably stable zone of gravitational equilibrium. That means the dark matter halo has to be extraordinarily symmetric, with minimal distortions or substructure. Dark matter halos are rarely that perfect. They contain lumps. They contain distortions from past accretion events. Even modest halo asymmetry would warp the ring, introducing ellipticity. But Hoag's ring is so circular that even minor deviations would be noticeable. This implies either an improbably smooth halo or a formation history that somehow eliminated asymmetries over billions of years, while preserving a fragile ring that should have been disrupted by the same process. Other galaxies with rings do not have this level of precision. Collisional rings show expanding waves. Resonance rings show oval distortions linked to bar patterns. Polar rings show strong kinematic decoupling. Hoag's object fits none of these categories. Its velocity structure is too balanced. Even the line of sight velocities across the ring show symmetry difficult to generate without a disk plane. Then there's the matter of timing. The core is very old. the ring is pretty new. This means that the structure we see now must have been dynamically stable for a long time, long enough for the core to relax, but recently changed enough to start the formation of new stars. What makes it possible for a system to stay stable for billions of years and then go through a recent event that doesn't change its shape or movement? Theories immediately disagree with each other. Either the galaxy has been quiet for a very long time, or the ring was formed not long ago by something. However, the data supports both of these ideas at the same time. Another argument proposes that the ring's gas gradually accumulated through gentle accretion from the intergalactic medium. That might explain the absence of violence, but not the ring's extreme symmetry or razor-thin orbital width. Accretion generally forms extended, irregular outer disks. Hoag's object instead consolidated gas into a narrow ring, ignoring the enormous angular momentum variations typical in filament-fed inflow. Think about the orbital evolution problem. Stars' paths change over a few billion years because of interactions, scattering, and dynamical drag. The ring needs to get thicker, it needs to get patchy. There should be no more space. The gap is still empty, the ring is still thin, and the whole dynamic structure is still perfectly lined up. The missing bullet galaxy problem. A small, fast-moving intruder galaxy that crashes through the disk of a larger system and causes a radially increasing density wave that squeezes gas into a ring is what causes a normal collisional ring galaxy. You have to use this bullet galaxy. The whole process is what makes a collisional ring. This is why, as soon as scientists saw Hoag's object for the first time, they started looking for the missing invader. There isn't a bullet galaxy though, not at all, not even a piece of a satellite lying off to the side. The area around it is not very dense. There is no companion that shows the right decline speed. Not a single dwarf galaxy is moving in the right direction. There are no signs of the tidal bending or brightness loss that would be expected from a galaxy that has recently interacted with a bigger neighbor. Not only is this a big problem, it's a problem that kills the collision hypothesis. Start with dates and times. In order for a head-on collision to create a ring as big as Hoag's, the invader galaxy would have to be pretty big and moving quickly. Once it hits something, the bullet should show up nearby, usually a few tens of kiloparsecs away. It should also have clear signs of how it changes over time, like tide stripping, asymmetric halos, or isophotes that are twisted. Deep imaging, on the other hand, shows a clean field around Hoag's object. No circles of debris, not any shells. There are no weak tide streams. The invader isn't even there. Some models propose that the bullet may have been a very small dwarf galaxy, but a dwarf cannot trigger a ring of this scale. The gravitational impulse would be insufficient. The mass ratio is wrong. To form a symmetric ring of young stars, the intruder needs to carry enough mass to drive a coherent outward wave. Hoag's ring is too large, too luminous, and too clean to have been formed by a low-mass object. Another explanation suggests that the bullet may have fully merged with the core. If true, the core should exhibit signs of that merger: asymmetry, rotation, metallicity anomalies, or dispersion features. Instead, the core is pristine. It is one of the cleanest, most undisturbed spheroids of its mass range. A merger violent enough to create the ring would also leave recognizable scars, and no such scars exist. Then we ask, could the bullet be the tiny background ring galaxy visible through Hoag's outer ring? No. Its distance is dramatically different. It is far behind Hoag's object, a coincidence of line-of-sight alignment, not a physical partner. Its redshift is wrong. It cannot be the culprit. What if the bullet flew through and escaped so quickly that it is now far away? Impossible. Even a high-velocity flyby leaves gravitational evidence: elongated stellar streams or gas compression wakes. None exist around Hoag's object. The environment is too quiet, too empty, too free of the scars expected from a drive-by impact. Could the bullet be completely dark, an object made of mostly dark matter? Theoretically, a dark subhalo could pass through a galaxy and trigger some compression, but simulations struggle to produce the level of coherent, luminous star formation seen in Hoag's ring through dark matter-only encounters. Dark halos lack the baryonic mass needed to generate the shock structures that ignite starbursts. And the balance is even worse. Most of the time, collision rings are not perfect circles. Because the contact is never exactly in the middle, they are often elliptical or warped. The invader is always off by a certain amount of angle. However, Hoag's ring is almost unbelievably round, with differences that are so small they are hard to measure. It is very unlikely that a collision that is perfectly centered will produce a ring that is perfectly round and has no leftover asymmetry. This is especially true if the intruder galaxy can't be found. The missing bullet problem is not a small loose thread. It is a foundational contradiction. If Hoag's object formed through collision, the bullet should be visible, detectable, or at least inferable from debris. But the universe offers nothing. No candidate, no evidence, no forensic trail. And that's when astronomers began checking the outer gas halo for clues, and found something even stranger. The hydrogen superring no one expected. Radio wave maps of the neutral hydrogen envelope in Hoag's object show that it breaks models. The visual ring is what draws the eye to the object. Radio telescopes were used to look at the galaxy, and what they saw was a long H1 structure that was much bigger than the visible star ring. This isn't just a dim disk on the outside. It is a huge, spread out but surprisingly unified pool of gas that wraps around Hoag's object like a ghostly halo and goes out tens of thousands of light years beyond the bright ring. This outer hydrogen ring creates a fundamental problem for nearly every proposed formation scenario. In collisional models, the impulse from a bullet galaxy pushes gas outward, creating a single expanding ring. But that ring should fade, distort, or fragment as it grows. It should not settle into a stable, symmetric superring that persists long after the impact wave has crossed the galaxy. Collisional simulations simply don't produce two rings, one optical and one hydrogen, where both remain so cleanly defined and aligned. The hydrogen structure is also too massive. It contains far more gas than the bright ring, yet shows no strong evidence of star formation at its edges. Normal galaxies with abundant H1 gas form stars when the density surpasses a threshold. But Hoag's outer gas stays diffuse, untriggered, and poorly organized for collapse. That suggests either A, something prevented fragmentation, B, the gas was accreted slowly and never densified, or C, the gas was once part of a larger disk that was stripped or reorganized. Option C is the one that should make the most sense, except it doesn't. If Hoag's object once had a full extended disk, the faint remnants of that disk should still be visible. Even ultra-faint stellar halos, warped outer regions, or dispersed clusters would appear in deep imaging. Nothing appears. The optical signal outside the bright ring drops off quickly, leaving only the hydrogen map to reveal what used to, or still might, exist beyond human sight. This superring raises the angular momentum question. Gas cannot simply float into a perfect toroidal distribution without inheriting an angular momentum profile from a disk or interacting system. Yet, the kinematics show no strong rotational shear or evidence that the hydrogen is part of a pre-existing disk plane. Instead, the velocity field is smooth and gently rotating, almost like a remnant structure left behind after a process that rearranged matter into a near-circular shell. Cosmic accretion over a long period of time, with strands feeding gas into a stable circular orbit, is one hypothesis. But harmony doesn't happen very often with filament growth. It makes clumps, streams, and flow patterns that aren't normal. That kind of irregularity doesn't show up here. Hoag's superring is just too cool to have formed by gas falling randomly. Another idea is that the hydrogen is the outer layers of a disk that was drained only near the center. Selective evacuation, on the other hand, needs a central cause, which could be an AGN, a huge starburst, or a collapse event. There are no AGN, starburst signs, or radial shock features on Hoag's object, which would mean it has a strong center clearing. The galaxy's superring looks more like it was always there than like it was cut by violence. There's also the chemical angle. Measurements suggest the hydrogen has moderate metallicity, not primordial, not extremely enriched, implying long-term association with the galaxy rather than recent external acquisition. That means the hydrogen reservoir has likely been part of the galaxy for billions of years. If so, why didn't it collapse into a disk? Why didn't it form stars? And why did only the inner boundary ignite into a bright young ring? One explanation is that Hoag's object's gravitational potential is extremely low in its outer parts, which keeps the hydrogen from collapsing. But this goes against the need for a smooth, symmetric rim that can support the circular stability of the ring. If the potential isn't very strong, the patterns should be less uniform and patchy, not like a torus with a clear inner edge. The hydrogen superring seems to be steady, which makes things even more complicated. On the timescales of the universe, diffuse gas tends to move, get denser, or circle inward. But Hoag's H1 structure looks like it has stayed put for billions of years, long enough for the core to form and the ring to catch fire. A structure this steady that doesn't show any signs of instability is very rare in galaxies that are far apart from each other. The hydrogen tells a story that is different from all the others. It looks like Hoag's object has two galaxies inside it, an old, calm, elliptical-shaped core and a large dead gas system on the outside that never formed a full disk. The bright ring is the edge between these worlds. It shows the radius at which stabilization breaks down and collapse is possible. The geometry too perfect for nature. Half of the puzzle would be gone if Hoag's object had even one bigger symmetry, like an elliptical distortion, a bent ring, or a core that wasn't in the middle. But the shape of the galaxy is so exact, so mathematically clear, that in the field of astronomy, people joke that Hoag's object looks like a galaxy someone drew in CAD. The outer ring is almost perfectly circular, with deviations so tiny they approach the measurement limits of current instruments. The core is centered with astonishing accuracy, no measurable displacement, no tilt, no rotational offset. Even galaxies formed in controlled simulations rarely achieve this level of symmetry. Nature almost never produces perfect circles at galactic scale. For a ring to be this circular, the gravitational potential must be extremely symmetric. Dark matter halos are never perfectly smooth. They acquire lumps from accreted substructure and perturbations from minor mergers. Yet Hoag's ring shows no signs of such disturbances. Even ultra-small halo distortions could warp the ring, introducing ovalization or radius variation. Nothing of the sort appears. The ring's radius is consistent across all observed angles, as though sculpted. The gap intensifies this symmetry problem. If the ring were slightly elliptical, or if the core were offset by even a few hundred parsecs, the gap would vary in thickness. That's not what we see. The annulus is uniform, a near-perfect circular void. This level of concentric alignment is so rare that statistical models place the odds extremely low unless formation conditions were artificially constrained or stabilized over long timescales. Another geometric issue emerges when considering vertical structure. Rings often thicken vertically due to gravitational interactions, turbulence, or warps. Hoag's ring remains thin. Its vertical height is difficult to measure directly, but its brightness profile suggests remarkably low scatter. A ring this thin requires a stable chilled gas layer and minimal vertical heating, conditions difficult to maintain without a disk to regulate them. Consider the core. Ellipticals are rarely perfectly spherical. They show flattening, triaxiality, or rotation-induced deformation. But Hoag's core is shockingly round. Its shape does not match that of a disturbed galaxy, nor that of a slowly evolved disk that puffed up over time. It appears more like an isolated elliptical that avoided major interactions for billions of years, contradicting the idea of a recent event that formed the ring. After that, there is the relative orientation. Any small tilt between the intruder's path and the center plane would twist the system if the ring formed from a collision, if the ring was made from a bar resonance. Any flaws in the way the bar broke down would cause the ring to be distorted. If the ring formed by growth, the direction of the flow would make it uneven. There is none. It looks like everything is just right. Astronomers have attempted to quantify this precision using isophotal fitting, radial profile modeling, and Fourier decomposition. The results all point to the same conclusion. Hoag's object is an extreme outlier in circular symmetry. Even galaxies engineered in high-resolution simulations rarely stay this symmetrical once you add real-world physics, feedback, turbulence, dark matter substructure, and time. When you think about how long things last, the math gets even stranger. Making a perfect ring isn't hard for a short time, but keeping it that way is hard. Over billions of years, tidal forces, halo distortions, and interior movement should cause changes that can be seen. But Hoag's ring is still perfect. Either A, the universe is very young, which isn't possible because the H1 superring is stable, or B, the universe has been very stable for a very long time, which isn't possible because the young stars were formed not long ago. The failed bar hypothesis that should have worked. A clean circular ring would most likely be caused by some kind of bar-driven resonance in almost any other galaxy. In disk galaxies, bars are typical structures. The gravitational force they make can push gas into narrow rings at certain resonant sizes. Often when a bar breaks apart, either through internal evolution or contact, the ring stays behind as a reminder of how it used to be structured. This seems like the right way to fix Hoag's object on paper. It neatly explains the symmetry, the small band where stars are formed, the stable path, and the fact that the ring is younger than the core. But reality doesn't want to play along. Bar-driven rings depend on the existence of a disk. A bar is not a standalone structure. It is the elongated instability that forms when a rotating stellar disk becomes gravitationally elongated in one direction. Hoag's object shows no disk at all, not even the faintest surface brightness feature that could indicate a dissolved or heavily heated one. Deep imaging fails to detect residual spirals, broken arm fragments, asymmetric halos, or low-level dust that would normally survive bar dissolution. Instead, the core presents as a nearly perfect spheroid, devoid of the flatness and rotation that a bar-bearing disk would once have exhibited. The kinematics make the situation worse. A galaxy that once hosted a bar should carry kinematic scars in the form of residual rotation or distinct orbital families left behind by the bar's influence. Observed velocity dispersion in Hoag's core matches that of a pressure-supported elliptical, not a rotationally supported disk remnant. Even subtle rotational signatures that could hint at a long-dead bar are absent. The stellar orbits inside the core follow a randomized pattern common to early type galaxies, not the structured motions expected from a heated disk. The metallicity gradient adds another layer of complexity. In a bar dissolution situation, the center area should have a pattern of chemical enrichment that matches how stars formed in the original disk. Instead, Hoag's core has the chemical makeup of an old ellipse, which suggests that stars formed quickly in the beginning instead of slowly becoming more dense like in barred spirals. This goes against any theory about the galaxy's past that says it had to go through a long disk phase in order to make and keep a bar. The geometry also fights the bar hypothesis. Resonance rings formed from bars rarely appear perfectly circular. They tend to retain the oval shape imposed by the bar's elongated gravitational potential. Even long after dissolution, the ring preserves some level of ellipticity. Hoag's ring does not. It is as circular as observational precision allows, implying an extraordinarily symmetric potential. Such symmetry would not emerge naturally from a system that once had a strong non-axis symmetric component like a bar. Even if one bends the scenario further by proposing a bar that vanished billions of years ago, another issue arises. The ring is too young. The core is ancient, but the bright blue stars in the ring are only a few billion years old. This timing mismatch means that if a bar created the ring, the bar must have dissolved recently. Yet the core shows no signs of recent dynamical disturbance. A recently dissolved bar would leave behind transitional features or distortions that simply do not exist. Gas distribution deepens the contradiction. Bar-driven rings form when gas accumulates at resonances. But Hoag's object contains a massive extended hydrogen superring that stretches far beyond the optical ring. This reservoir seems unrelated to any bar mechanism and lacks the density structure that would support bar-driven accumulation. Bars tend to funnel gas inward or outward, but they do not produce the kind of large, diffuse, stable hydrogen envelope observed around Hoag's object. The bar hypothesis is beautiful, well known, and backed up by a lot of evidence from other ring-bearing galaxies. Other places it works. This should work. But Hoag's object doesn't have any of the necessary conditions. It doesn't have a disk, a spin, a bar scar, any metallicity leftovers, any geometry leftovers, or any kinematic memory. The chemical clues that don't line up. In the field of galactic archaeology, chemical makeup is one of the most dependable tools. Astronomers can figure out how stars form by remembering how metallic the gas cloud they came from was. This lets them piece together evolutionary histories long after structural evidence is lost. The chemistry of Hoag's object should be able to tell an easy story. Either the ring and core formed from the same parent gas, or they formed separately through interaction or accumulation. There is a third, inconsistent story that the chemical signatures show that doesn't fit with any known route. The core exhibits a metallicity appropriate for an early type elliptical, relatively enriched, consistent with rapid early star formation and quenching. This is expected for a spheroidal system that formed its stars in the early universe before gas supply dwindled or feedback shut down further star formation. Fine so far, nothing unusual, but the ring shows a metallicity level that is neither strongly enriched nor strongly primordial. It sits in an awkward middle zone. This suggests the gas that formed the ring is not purely external, not purely internal, and, critically, not fully consistent with gas that remained dormant in the galaxy for billions of years. If the ring formed from internal gas expelled outward by a collision, its metallicity should match or exceed the core's, because the core's enriched gas would dominate the expelled material. But the ring's metallicity is slightly lower. This is impossible under a simple collision model. If the ring formed from external gas accreted from cosmic filaments, it should have significantly lower metallicity than observed. Filamentary gas is chemically primitive compared to the enriched environment of a mature galaxy. Hoag's ring is not nearly primitive enough for that scenario. If the ring formed from a small merging companion galaxy, its metallicity should show distinct signatures, either too metal poor for a dwarf, or enriched at a rate inconsistent with the host galaxy's early chemical evolution. But the ring's composition does not match dwarf signatures, nor does it match the chemical profile of typical gas-rich minor mergers. The way the elements are spread out adds to the tension. Oxygen, magnesium, neon, and other alpha elements show up at amounts that suggest they have had different enrichment experiences. Some of the gas looks like it was changed by big stars, while other parts act like they were never passed through the generations of stars. This mix shouldn't happen in a single origin case. The ring also shows a smoother metallicity gradient than expected. Rings formed through collision usually exhibit chemical asymmetries because the expelled gas clumps differently around the expanding wave. Resonance rings retain traces of chemical inheritance from the bar or inner disk. Accretion rings show patchy compositions reflecting irregular inflow. Hoag's ring instead displays an evenly mixed composition, as though the gas were homogenized before star formation began. This leads to an unsettling possibility. The ring's gas was rearranged or redistributed long before it ignited. Something may have swept gas outward and allowed it to settle uniformly, smoothing chemical differences before star formation began. But no known mechanism, collision, resonance, or accretion, naturally homogenizes gas at this level without leaving structural or kinematic evidence. The amounts of nitrogen and carbon create another chemistry problem. These elements show how long-lived stars change over time, and the amount of them in a galaxy can show whether it went through slow enrichment or fast bursts. It looks like the core went through fast early bursts. The ring looks like it went through a mix of enrichment processes. It's as if some of the gas went through a slow, quiet chemical evolution, and some came from material that was enriched in quick, massive star cycles. It is the chemical equivalent of a mismatched fingerprint. The core and ring do not share identical ancestries, but neither do they fully diverge. They occupy a liminal zone between same origin and different origin, and no standard galactic model allows for that without invoking events that, based on all other evidence, did not happen. Chemists say that there were two developmental paths going on at the same time: an old core that formed in the early universe and a newer ring made of gas with a complicated past. But the process that connects these events is still not clear. Something precisely moved, mixed, and put that gas in place, but there are no structural signs of what it did. The star formation timeline that breaks the clock. A galaxy's evolution can be easily figured out by looking at its communities of stars. The stars show the order of events. Their ages show when the gas stopped moving, when it resumed moving, and when it stopped again. The history of a normal ring galaxy looks like this: an old core, a wave-triggered starburst in the ring, and populations dying out in the gap. Everything in that series is messed up by Hoag's object. Its core, ring, and gap don't fit into any one timeline, so scientists have a story that is like a deck of cards that has been mixed up. The core is the easiest part. Its stars are ancient, billions of years old, with signatures of early universe formation and rapid quenching typical of small ellipticals. Nothing about the core's age profile is surprising on its own. It is what surrounds that core that breaks the narrative. The ring, packed with bright blue stars, has a formation age measured in the low billions of years, drastically younger than the core but not young enough to represent a recent galactic trauma. If the ring had been created just a few 100 million years ago by a head-on collision, it would glow with extremely young, extremely massive stars in distinct knots. Instead, the ring presents a mixed age population that suggests extended or recurrent star formation rather than a single explosive episode. At first glance, this might imply a slow accumulation of gas followed by gradual ignition. But the coherence of the ring contradicts that. Slow accumulation produces patchiness. It introduces multiple ignition points spread across the ring. Hoag's ring behaves more like a tightly regulated starburst that began nearly simultaneously around the entire circumference. The smoother distribution is more consistent with a synchronized event, yet the ages do not reflect the intensity of a synchronized starburst. Instead, the age spread suggests star formation that was sustained but not violently triggered, as if the gas lingered at a stable density threshold for a long period before forming stars at a leisurely but consistent rate. The gap creates an even more serious problem with time. If the ring formed a few billion years ago, the stuff in the gap should show ages in between. Stars moving away, stars being born in gas that isn't clumped together, pieces of a faded disk, or at least signs of a bar or spiral structure that is breaking down. Instead, the gap acts like an area where stars haven't formed in a very long time. There isn't a clear group of people in the middle age range, which shows that the gap has been empty for a very long time, longer than the ring has been around. It seems that the ring didn't push gas out of the gap, since there wasn't much gas there to begin with. This lack of intermediate age material is a direct blow to collision models, which require the inner region to have once contained gas that was pushed outward. If no such gas existed, the ring cannot be the result of a collisional density wave. And if the ring is not the outcome of a collision, then the timeline becomes even harder to resolve, because the galaxy must have maintained this empty interior region, while still acquiring, stabilizing, and igniting the gas that now forms the outer ring. Another complication arises from the metallicity distribution across the ring. The chemical mixing suggests a long preparatory phase before star formation, where gas accumulated and homogenized. That implies that the ring's gas was present long before the stars we see today formed. But if the gas was present for billions of years, why did star formation begin only recently? Galaxies with stable gas reservoirs normally form stars steadily unless something suppresses collapse. Hoag's object shows no evidence of such suppression. There is no active black hole, no intense stellar feedback, no obvious dynamical heating that could have prevented gas from collapsing earlier. It is as if the gas waited, stable, uniform, unperturbed, until a trigger that left no detectable trace. The architecture of the ring requires a catalyst, but the timeline refuses to show what that catalyst was. The star formation history of Hoag's object also clashes with the behavior of the extended H1 superring. If the outer reservoir of hydrogen has been present since early cosmic times, a normal galaxy would convert that gas into stars over time. But Hoag's object did not. It instead allowed the gas to remain cold and inactive, then somehow induced fragmentation at only one precise radius. This radius corresponds exactly to the visible ring, suggesting a boundary condition set by gravitational potential, gas density, or dynamical resonance. But none of these possibilities fit neatly with the observed kinematics. There is a paradox in the order of events. The core died young, became stable, and turned into a relic. The ring formed a long time after the birth, but it did so in a way that looks like coordinated firing, but doesn't match the chemical or physical features of a violent birth. The gap stayed empty the whole time, which went against every process that would have linked the core and ring into a single developmental path. The dark matter halo that refuses to behave. Dark matter halos are where galaxies live. How stars move around, how gas settles, how structures grow, and how stable a system stays are all controlled by these halos. The halo should be the part of Hoag's object that brings order to the chaos. It should be a gravity backbone that explains why the core is calm, why the ring spins smoothly, and why the galaxy has been around for billions of years without becoming uneven. Instead, the ring adds more problems that make it even harder to put Hoag's object into a category. The first contradiction lies in the halo's symmetry. The ring's near-perfect circularity implies that the underlying dark matter distribution is extremely spherical. Even mild asymmetries in the halo would introduce measurable distortions in the ring's radius, shape, or brightness. Yet the ring is so perfectly circular that the halo must be almost mathematically smooth. But halos are rarely smooth. They form from hierarchical mergers, accreting clumps of material over cosmic time. Each merger, even a minor one, leaves density variations that alter orbital structure. Hoag's halo seems to lack this history, even though its core displays the characteristics of a galaxy that formed early and likely experienced environmental shaping. The halo also lacks any indication of recent disturbance. If the ring were the product of a collision, the halo would carry signatures of that event. The gravitational shock would not disappear. Dark matter is collisionless, so it retains memory of perturbations longer than baryonic material. A major impulse should leave behind a distorted potential, but the rotation curves derived from stellar and gaseous motions across the ring show no such distortions. The next contradiction concerns mass distribution. The halo must be massive enough to stabilize the ring, keeping it in its razor-thin orbit and preventing vertical heating or radial drift. Yet, it must be gentle enough not to collapse the outer hydrogen reservoir or trigger star formation beyond the ring. This requires a finely balanced potential well, deep at the ring's radius, shallow outside it, and smooth throughout. Such balance is extraordinarily rare in nature and nearly impossible to produce without invoking a long evolutionary history with specific tuning. But every tuning mechanism astronomers consider introduces conflicts with the observed chemistry, star formation timeline, or kinematics. The halo also contradicts the idea of bar-driven evolution. Bars form when a disk within a halo reaches a threshold of dynamical instability. But Hoag's core lacks the disk needed to generate a bar, and the halo shape indicated by the ring's geometry is too round to produce the non-axisymmetric torque that bars require. Even if a bar dissolved in the past, halos normally show residual triaxiality associated with such evolution. Hoag's halo appears too idealized for that scenario. Another problem emerges when modeling the gravitational potential needed to maintain the empty gap. The gap is too clean and too stable to exist without some type of barrier, either a resonance boundary or a zone with insufficient surface density for star formation. If the halo creates such a boundary, that boundary would likely produce corresponding signatures in the outer hydrogen ring. But the hydrogen envelope shows no abrupt structural change at the gap radius. Instead, the gap appears only in the stellar distribution, not in the halo's gravitational imprint. There isn't much help in simulations. Almost all attempts to include Hoag-like systems in cosmic models fail for the same reason. Either the halo gets too bumpy, which breaks the symmetry of the ring, or it forms a disk too easily, which goes against what we see as a spheroidal core. When the parameters are just right, the outer hydrogen distribution falls too quickly inward or becomes unstable long before star formation starts to happen at a single narrow radius. The halo also raises questions about angular momentum. Hoag's object rotates coherently, yet its core shows little rotational support. This combination requires a system where angular momentum resides primarily in the outer regions, not in the central spheroid. Such angular momentum profiles occur in galaxies with strong merger histories or extended accretion phases, but those processes inevitably leave structural fingerprints. Hoag's object shows none of them. The dark matter halo looks more and more like a perfect gravity mold for the messy processes that shape galaxies. The more experts look at it, it acts like it was formed by itself and hasn't been touched in billions of years. But it still made a ring that is too young, too symmetrical, and too exactly placed to fit such a calm evolution. Because the next layer of evidence suggests Hoag's object might belong to a formation pathway we have never successfully modeled. The formation pathways that all fail. When scientists are done comparing Hoag's object to all the different types of ring galaxies they know of, things look so bad that it's almost funny. There are three main ways that rings form in galaxies: collision-induced rings, resonance-driven rings, and accretion-built rings. All three work perfectly in dozens of other systems. There are decades of models, case studies, and observational records that back up each route. Still, none of them can make a copy of Hoag's object without breaking at least a few important physical rules. In very few situations do all known answers go against the facts. The collisional route is the first one that falls apart when looked at more closely. Collision rings are very dangerous. After they go, chaos follows. The invader galaxy sends out an increasing density wave that squeezes gas into a ring, but the core is always thrown off. Shocks show up. There is turbulence. Tidal garbage stays around. Even friends who live far away show signs of being upset. No one is shown by Hoag's object. It's quiet at its core. It doesn't have a gap. It's empty. The area around it is quiet. The bullet galaxy that is missing is not a small mistake. It is the most important piece of proof that a collisional ring should have. And the fact that it is absent proves the whole mechanism is wrong. The resonance pathway requires a bar, because a bar reshapes orbital families and induces gas to migrate to resonant radii. Without a bar, there is no resonance. Without a disk, there is no bar. Hoag's object contains neither. Even if the bar dissolved, the core should carry rotational memory or a flattened shape, and neither is present. A resonance origin also fails because it cannot account for the massive outer hydrogen reservoir. Resonant rings form within disk galaxies, not in systems with giant, diffuse hydrogen envelopes, lacking corresponding stellar disks. The accretion pathway offers more creative wiggle room. Gas can fall inward from filaments, build up in toroidal flows, and ignite star formation once densities reach threshold. But filamentary accretion is messy. It introduces angular momentum variations, clumpy infall regions, and asymmetries. Hoag's object is too symmetric, too clean, too circular to reflect such chaotic assembly. More importantly, the ring's metallicity is too high for fresh filament gas, but too low to be the expelled internal gas of a collision. It sits in a limbo zone that frustrates the simple story accretion should provide. Some researchers propose hybrid models, blending features of collisions and resonances, but hybrid models require contradictions to coexist. A collision strong enough to move gas outward should disrupt the core and halo, destroying the symmetry needed for resonance processes later. A resonance strong enough to shape a ring requires a bar that never existed. A hybrid event that first created an elliptical core then produced a resonance ring contradicts the timeline of the ring's star formation history. Every attempt to splice multiple origins together ends with internal inconsistencies. Other ideas stretch creativity further. Perhaps Hoag's object is a polar ring seen face-on. But polar rings have distinct kinematic signatures because the ring orbits in a plane perpendicular to the main galaxy. Hoag's core and ring rotate in the same gravitational plane. The velocities do not match a polar configuration. The face-on view argument dissolves once kinematics are included. Another idea imagines an ancient giant disk that was stripped of its stars but kept its gas. But stripping mechanisms require cluster environments or massive interactions. Hoag's object sits in an isolated region. There is no stripping force available, and stripped disks leave behind sharp tidal remnants that do not fade easily. None appear here. A more unusual theory says that the ring was made by a long-lost neighbor galaxy that broke apart slowly around the core, putting gas into a narrow circular band. But satellites break up in strange ways. In their wake, they leave behind lines, shells, and mechanical errors. They don't often make rings of gas that are regular and small enough to form a perfect symmetry. Whenever a plausible mechanism is proposed, one of the three observational pillars, kinematics, symmetry, chemistry, destroys it. The galaxy behaves as though it formed through a mechanism that left no scars, built perfect geometry, maintained a stable gap for billions of years, and ignited star formation only at a specific radius, without disturbing the massive outer hydrogen reservoir. It's like a device that works perfectly, but doesn't come with any directions on how to put it together. Not that one model fails, but that all of them fail is what's most confusing. Hoag's object acts like a system that has been tweaked beyond what is possible in natural galactic evolution. The way it forms must follow a stricter set of rules than anything seen in current cosmological models. The simulations that can't recreate reality. Astrophysicists use models to find answers when observational data won't do the job. Simulations have been able to very accurately show rings, spirals, bars, mergers, and accretion flows. With enough factors, it is possible to describe even strange shapes like collisional spokes, warps, and polar rings. Hoag's object shouldn't be any different. It should be another high-resolution challenge. Change the mass ratio, the shape of the halo, the collision angle, the inflow conditions, or add true changes to the gas's density. A program should end up with something that looks like Hoag's object in the end. Simulations that assume a collision produce rings that expand unevenly, warp under halo irregularities, or fragment into clumps. None create a stable, razor-thin ring that remains circular for billions of years without residual distortions. When researchers try to force symmetry by idealizing the halo, the core becomes unrealistically disturbed. When they tune the impact parameters, the ring becomes too young or too irregular. No run produces a calm, relaxed core surrounded by such a perfect ring. Simulations that rely on bars run into a different set of failures. Without a disk, no bar forms. If a disk is added artificially, the ring forms but inherits the bar's elongated symmetry, and even after bar dissolution, the ring remains oval. Attempts to smooth the ring by introducing feedback or long-term dynamical evolution create vertical thickening and patchiness that contradict the observational data. The chemical gradients also fail to match. Synthetic rings formed from dissolved bars, do not show the homogeneity seen in Hoag's object. Simulations of filamentary accretion introduce too much randomness. Inflows create angular momentum variations that prevent a single narrow ring from forming. The outer hydrogen envelope in these models becomes unstable, collapsing inward or fragmenting long before the ring can form. Even carefully tuned inflows fail to produce the mixture of metallicity and structure observed in the galaxy. With high-resolution multiphase gas dynamics that let gas cool, collapse, and move in ways that older models couldn't, some teams have tried to solve the problem by hand. These models sometimes look a bit like Hoag's object. A ring forms, the core stays mostly still, and gas builds up around a narrow radius. But the ring bends or gets thicker over time, or stars fill in the space, or the outer hydrogen breaks apart, or the system changes over time so that it becomes a disk galaxy instead of a sphere in the middle. No simulation has reproduced the combined constraints: a perfectly round ring, a barren gap, a fossil core, a massive hydrogen superring, matched kinematics, mixed metallicity, and long-term stability. The difficulty is not computational. Modern simulations can model galaxy evolution with exquisite detail. The difficulty is conceptual. The ingredients needed to form Hoag's object contradict the ingredients needed to maintain it. Simulations can reproduce pieces of the puzzle, but never the entire system. When they match the geometry, they break the chemistry. When they match the chemistry, they break the kinematics. When they match the kinematics, they break the timeline. The more parameters researchers tune, the clearer the truth becomes. The galaxy's properties lie at the intersection of multiple incompatible formation channels. Hoag's object behaves as though it is the endpoint of a process that doesn't exist in current cosmological models. It is too orderly for collision, too structured for accretion, too symmetric for secular evolution, and too young in its ring to reflect steady long-term gas dynamics. It's not that Hoag's object is impossible. Simulations fail because the rules we use to make galaxies can't make something so tightly bound without leaving traces that can be seen. In the tightest technical sense, the galaxy is an outlier. It is a system whose traits are not in the solution space of current models. The Hoag-type galaxies that almost explain it. As soon as scientists realized that models could not recreate Hoag's object, they knew what to do next. They had to look for cousins. If nature made this building just once, it could have made it more than once. There might be a larger group of Hoag-type galaxies, rare but not unique. If enough cases are logged, trends might start to show up that show how the missing formation process works. It looked like it would work for a short time. A few galaxies seem to have Hoag's unique structure: a spheroidal core, an outer ring that wasn't attached, and a clean circular space between them. Some candidates had center cores that were not completely round, showing weak elongation or disk structure that was still there. Others showed rings that were slightly irregular or not evenly bright, which suggested that the gravity field underneath was not perfectly balanced. Some of them had rings that weren't as smooth or straight as Hoag's. They were too thick, twisted, or patchy. Some of them had marks on them from bars or disks inside that suggested a very different genetic past. The idea of a shared beginning was called into question by a few that showed metallicity slopes. The most famous cousin is UGC 4599, often presented as the closest match to Hoag's object. It features a central spheroid and an outer ring that, at first glance, mimic the structure of Hoag's. But deeper observations show that UGC 4599 contains a faint, subtle bar-like distortion in the core and mild asymmetry in the ring that betrays a different evolutionary path. The gas distribution in UGC 4599 is not perfectly aligned with the ring. Its star formation history contains evidence of multiple bursts rather than the smoother, more uniform profile observed in Hoag's object. It resembles Hoag's object in shape, but it is not a genuine analog. Other candidates fall even further apart. Some rings show clear tidal debris that link them to past interactions. Others reside in environments far richer than Hoag's sparse surroundings, making interaction-driven origins far more plausible. Still others contain multiple nested rings with no clear gaps, implying complex secular evolution rather than the razor-thin boundary observed in Hoag's object. The more researchers searched, the more it became clear that Hoag's object sits at the extreme end of a spectrum, not comfortably within a category. This creates an interesting tension. Hoag's object is not entirely alone. It does not break genus-level classification. It is not a mythical one of one, but it is a species with no robust family tree. The nearest relatives resemble it in coarse outline, but diverge in every crucial structural detail: symmetry, ring thickness, gap emptiness, metallicity uniformity, and long-term stability. They are almost Hoag-like, but almost solves nothing. Even the statistical rarity presents a challenge. If ring galaxies are already uncommon and Hoag-type objects are a fraction of that fraction, the formation mechanism must be something that almost never happens. Yet whatever event shaped Hoag's object also preserved the system so delicately that it survived for billions of years without distortion. Rare events tend to leave scars. Hoag's object shows none, because the galaxy's isolation turns out to be the most confusing part of all. The environment that removes every easy answer. Galaxies are formed by the things around them. It is the dense groups that cause disturbance, strip gas, mergers, and big changes. Asymmetry and long-term secular evolution are driven by connections that aren't as strong when groups are loose. Galaxies that are far away from each other change slowly and steadily, following paths that are usually slow and predictable. If you knew this, you might think that Hoag's object's surroundings would give you signs. Not only does the surroundings not make things clearer, it makes the puzzle harder. Hoag's object resides in a low-density region where significant interactions are rare. This isolation eliminates the simplest explanations immediately. A quiet environment cannot support the major mergers required to build a classical elliptical core. It cannot support the stripping or tidal heating necessary to erase a disk. It cannot produce the gravitational impulse needed for a collisional ring. It cannot sustain the complex torques necessary to form a bar-driven ring. Environmental factors that could generate such features are simply absent. Another paradox is created by this isolation. The core that looks like a fossil seems to have been made during an early violent stage of assembly. Today, though, there are no signs that such things happened close. In areas with higher galaxy densities, where the chance of collision is higher, galaxies that go through strong early mergers typically dwell. The Hoag's object is by itself. If it was caused by violent ancestral events, they must have happened in a different setting a long time ago, and then people had to move to a calmer area. But galaxies don't just move tens of millions of light years from places with a lot of stars to places with few stars without leaving behind partners or junk. The object in Hoag sits by itself, calmly, without anyone else around. The environment also challenges the extended hydrogen halo. If the galaxy had undergone interactions early in its life, the outer gas reservoir would likely have been stripped, distorted, or compressed. Instead, the hydrogen superring appears undisturbed, as if it has never experienced a disruptive external force. This suggests long-term environmental stability, yet the core suggests a tumultuous early life. These two conditions contradict each other in standard cosmological models. Even the clean symmetry of the ring implies environmental stability. A galaxy in a populated region would experience mild tidal interactions regularly. These interactions would warp the ring, distort the gap, or perturb the halo. Hoag's object shows no such scars. Its outer regions remain too perfectly balanced to have survived any substantial tidal influence in the past few billion years. The galaxy's isolation also takes away the possibility of an intruder galaxy that is hiding or has long since left. People who break in might merge completely, move away quickly, or blend into a busy background in places with a lot of people. But in a place as quiet as Hoag's, it would be easy to spot a stranger. It's not very clear in the sky around Hoag's object. Every galaxy that talked to it would stand out. Not one does. The emptiness of the environment even affects the potential for cosmic accretion. Although galaxies can still accrete gas in isolation, the inflow rates are lower and the streams less coherent. Forming a massive hydrogen superring through such processes would require consistent, long-term inflow with stable angular momentum, a configuration that is rare in sparsely populated regions. Again, the environment contradicts the structure. This leads to a bigger problem. Hoag's object acts like it has been actively protected for a very long time, but it also acts like it went through a recent well-tuned restructuring event, one that was strong enough to light the ring on fire and rearrange the gas without affecting the core or halo. It had to have been changed and kept safe, both quiet and crazy, stable and changed up. None of these factors can happen at the same time because of the surroundings. When you think about how stable the outer hydrogen reserve is, the paradox gets even stranger. In areas with more matter, radiation fields from other galaxies and close galaxies make scattered gas less stable, so it can't stay in one piece. Such gas can live longer in isolation, but over cosmic timescales, it still has a propensity to sink inward or break apart. The outside of Hoag's ring is still whole, almost frozen in time. The environment was meant to make the puzzle easier. Instead, it gets rid of all simple mechanisms. The slow, steady evolution path that leads to either a disk or a scattered spheroid should be followed by a galaxy that is by itself, like Hoag's object. It shouldn't make a ring that is exactly symmetrical, a gap that is very precise, a fossil core, and a long hydrogen rim that has been stable for billions of years. The background ring that should not be there. Nature added a feature that is so unlikely that it feels like a cosmic joke. Hoag's object was already very strange. At about 1 o'clock, inside the bright outer ring, there is a second ring galaxy that is much smaller, farther away, and perfectly framed inside the gap. Even though this background ring has nothing to do with Hoag's object physically, it creates a statistical oddity that is so big that scholars instantly wondered if it meant something, or was just a 1 in a million alignment. Every new observation proved that the small inner ring really is a background galaxy. Its light just so happens to pass through the empty space inside Hoag's ring very precisely. Astrophysicists are surprised by this accident, because line-of-sight alignments are not unusual, but alignments with such perfect geometry are. There is no small ring behind the core, or behind the bright outer ring, where it would be covered or mess up. It is right in the middle of the dark circle, which is the only part of Hoag's object where you can see almost everything. If there were even a few stars or bits of dust in the gap, the background ring would become blurry or disappear. Instead, the space acts as a sort of visual window, bringing out the small ring in a way that looks like Hoag's object was trying to frame it. When you think about how rare ring galaxies are, the similarity stands out even more. These shapes are not common. It should be very, very rare that you could find one through the opening of another. The small background ring is also well formed and easy to spot, which makes it an extremely easy target. The alignment is strange from a statistical point of view, not because it is impossible, but because there are very few ways that two clean, symmetric rings could meet in this way. The alignment is so fine that even small changes in how clear the dark gap is would have hidden it. But despite how tempting the coincidence seems, it does not provide a causal explanation for Hoag's object itself. The background galaxy is too distant, too faint, and too small to exert any gravitational influence capable of shaping a structure as massive as Hoag's. Its recession velocity places it far beyond any interaction scenario. The alignment has no dynamical relevance. It is a visual phenomenon only. But the very fact that the gap is transparent enough to make this alignment obvious says something important. The gap is genuinely empty, not just lightly populated. There is no diffuse dust obscuring the line of sight, no hidden stars thick enough to mask the inner ring. This emptiness strengthens the case that the gap is not a transitional region, but a stable, long-maintained structural boundary. The background ring also serves as a perfect natural probe. Its light passes through Hoag's object without significant reddening or extinction. Measurements confirm the absence of dust lanes or intervening gas filaments that one would expect in galaxies formed through major mergers or bar-driven evolution. The lack of absorption features further reinforces the idea that Hoag's object has avoided mechanisms that typically inject dust and gas into intermediate regions. It behaves like a system that has been remarkably clean for an extraordinarily long time. Some astronomers suggested that the alignment might reflect an observational bias rather than cosmic strangeness. Humans notice coincidences more readily when they are visually striking. But even after accounting for selection bias, the alignment remains statistically noteworthy. Yet the irony is that even such an improbable visual coincidence still leaves Hoag's object fundamentally unexplained. The background ring does not inform formation mechanisms. It simply highlights how pristine the central gap must be. The last theory: standing, an unmodeled evolutionary path. As astrophysics moves into its least comfortable area, when every standard process of creation fails and every near-match galaxy falls short, it admits that the current taxonomy of galaxy evolution may not be complete. Hoag's object makes us talk about this. It's not a galaxy that almost fits a model. It is a galaxy that constantly goes against the models. Everything we see seems to be there to make us question something. The perfect outer ring, the empty gap, the fossil core, the extended hydrogen halo, the mixed metallicity gas, the uniform dark matter potential, the isolated environment, and the unlikely geometric alignment. There are too many inconsistencies to think they are just random observations or odd accidents stacked on top of each other. One option is that Hoag's object might show a formation channel that hasn't been well described in models yet, possibly because the conditions that drive it aren't within the normal range of parameters we think galaxies work in. It may not have been a violent one-time event or a slow evolution. Instead, its structure may show a long, very stable multi-stage process that needs factors that aren't likely to be found in normal settings. One possibility is that Hoag's object evolved from an early compact elliptical that accreted a large gas reservoir extremely gently over billions of years. In such a scenario, the gas could settle into a toroidal configuration if angular momentum were injected uniformly through a long sequence of minor inflows. The problem is that minor inflows normally vary in direction and velocity, but if the inflows were unusually consistent, the gas could accumulate into a massive smooth ring before cooling sufficiently to collapse. Only when the gas reached a threshold density would the ring ignite in star formation. This could explain the ring's age and uniformity, but it does not explain why the gas would be mixed so evenly, nor why the outer hydrogen ring would remain stable for so long. Another possibility involves an early primordial halo with exceptional uniformity. If the dark matter halo were unusually spherical from the beginning, far more than typical halos produced by hierarchical merging, it could suppress asymmetry in the baryonic structures that formed later. Such a halo could theoretically stabilize a gas ring at a fixed radius, but cosmological models almost never produce halos this smooth naturally. Even if a rare halo formed with such symmetry, subsequent minor accretion events would distort it. Hoag's object seems to have avoided these distortions entirely. There is also a conceptual route that involves a slow radial migration that is caused by gravity resonances that are not caused by bars, but by early epoch vibrations in the halo. These would be weak, long-period modes that move gas outward very slowly and evenly, making a gap without the need for a disk or collision. In the end, gas would build up at a stable radius, where orbital overtones strengthen each other, creating a natural ring border. This is a beautiful thought, but it's hard to prove. At the moment, simulations can't keep these harmonic states going for billions of years, without outside disturbances messing them up. A fourth possibility considers that Hoag's object formed through a multi-phase evolution where different components were assembled at different epochs under entirely different physical regimes. In the early universe, the core may have formed rapidly in a turbulent region. Later, the galaxy may have migrated into a quieter region of space where slow accretion built up the hydrogen superring. Still later, a gentle inward collapse or subtle density shift ignited the bright ring. Each stage obeys physical laws individually, yet together they produce an improbable harmony that simulations rarely attempt because they require time-dependent environmental transitions. This scenario would require an incredibly specific cosmic history. What makes Hoag's object so difficult is not that these ideas are impossible, but that each demands conditions so precise, so isolated, and so stable that they barely align with known galaxy demographics. Yet Hoag's object is clearly real. It exists, which means the universe has at least one pathway that can produce a structure like this. The challenge is that the pathway has not been mapped, modeled, or observed in action. And that missing chapter becomes even more urgent to confront when new telescopes begin to uncover ring structures that make the mystery deeper, not clearer. The JWST surprise that complicates everything. For many years, Hoag's object sat in a quiet area of astronomy, mysterious but by itself. It was the kind of strange object that experts only look at every few years when new tools make images or spectra clearer. That changed when the James Webb Space Telescope turned on. Even though JWST wasn't made to solve the Hoag problem, its ability to resolve weak structure and trace cold gas showed us something more important. Ring galaxies are much more varied and complicated than earlier telescopes let us see. A new piece of information about Hoag's object has been found that makes it even more strange. One of JWST's first shocks was the discovery of a double ring system unofficially nicknamed the Cosmic Owl. This system contains two interacting galaxies whose overlapping gravitational waves have produced nested rings on scales previously seen only in simulations. The structure is chaotic, luminous, and clearly the result of a dramatic encounter. And that's where the trouble begins. The Cosmic Owl demonstrates how violent, multi-stage collisions can produce rings far larger and more ordered than earlier models predicted. The discovery expanded the menu of ring formation pathways, showing that under certain conditions, rings can form through hybridized mechanisms that blend collisional shocks with resonance effects triggered by secondary waves. The moment this was announced, some astronomers speculated that Hoag's object might finally make sense in the broader context. Perhaps Hoag's clean geometry was a faint echo of a far more complex series of interactions, a type of galactic evolution only now coming into focus thanks to JWST. But that hope collapsed almost immediately when the details came in. The Cosmic Owl's rings are bright with tidal structure, spokes, and asymmetry. Debris clouds arc across its outer regions. Its core exhibits clear kinematic distortions. Every part of the system screams interaction. It is the opposite of Hoag's object in every measurable way except the presence of rings. Even JWST's most refined ring detections complicate the issue. Many of the newly discovered rings form in galaxies with strong internal disks or evolving bars, features Hoag's object lacks completely. Others form in violent environments full of gas-rich fragments and interacting dwarfs, again unlike the pristine isolation Hoag inhabits. JWST has revealed that the universe can make rings far more easily than once thought, but it also shows that those rings carry scars. Their origins are written into their structures. Hoag's object remains the singular exception where the scars are absent. Another surprise from JWST comes from the distribution of star-forming clumps in rings across the early universe. Rings in younger, more turbulent epochs often appear patchy, asymmetric, and short-lived. A few are surprisingly smooth, but they form as part of rotating disks or bar-driven instabilities, not as detached structures with empty central voids. Even the rare clean rings JWST identifies still show faint dust, irregularities along the circumference, or gradients in metallicity that betray their origins. Hoag's object shows none of these hallmarks. JWST also measured cold molecular gas in ring galaxies with unprecedented sensitivity. These observations reveal how gas collapses, how it fragments, and how star formation proceeds. In almost every case, the early phases of ring formation are messy. Turbulence plays a central role. Shocks ripple through gas clouds and create fragmented filaments. Again, Hoag's object sits at odds with this broader picture. Its ring is uniform, its collapse history unusually smooth, and its star formation prolonged rather than explosive. If you look closely at JWST's ring census, you might find that Hoag's object is not really a ring galaxy after all. Some scientists are now wondering if the ring should be seen more as a border condition made by a special gravity potential, more like a standing wave than a structure that changes when things hit or flow into it. From this point of view, the ring exists because it's the size of the circle where gas can be compressed by gravity. This idea is somewhat supported by JWST's finding of wide, spread-out rings around huge halos, but none of these objects match Hoag's level of isolation or symmetry. While JWST has unveiled dozens of ring-like systems across cosmic time, every single one carries identifiable formation clues. Hoag's object carries none. The deeper the telescope peeks into the universe's ring population, the more Hoag's architecture stands out as an extreme, not as a variation. If anything, JWST has made the galaxy more anomalous by expanding the domain of what normal rings look like. Why does everything about Hoag's object look like it was designed? This is the one question that scientists keep coming back to. The paradox of precision that refuses to go away. When it comes to science, accuracy is often a sign. The idea of fixed gravity potentials is supported by symmetry. A slow expected evolution is indicated by tidy structures. Uniformity means that there is no disruption. Astronomers think that a galaxy that has these features went through a slow, well-known development process. This theory doesn't work at all with Hoag's object. It is so accurate that it goes against every assumed link. Precision leads to conflict instead of ease. Start with the perfect circle of the ring. In any typical galaxy, circular symmetry arises only when the surrounding gravitational environment is nearly ideal. That level of idealization is found in systems that have experienced little disruption, little accretion, and minimal merger history. Such systems also develop predictable radial gradients, like smooth transitions from dense cores to diffuse outskirts. Yet Hoag's object does not behave like a galaxy with a tranquil past. Its central core resembles an early type elliptical, a structure usually forged through violence. The ring implies a reorganization of gas on a massive scale. The hydrogen superring implies a long history of accretion or retention. Precision and violence should not coexist this seamlessly. The narrow, pristine gap between core and ring raises the contradiction even further. A ring formed through collision or bar resonance should leave behind fragmentation, dust, or residual material. A ring formed through accretion should exhibit signs of turbulence or irregular inflow. The gap should tell the story of what happened. Instead, it tells no story at all. It is empty, quiet, undisturbed. Even faint background galaxies shine through it without reddening. The gap is not a region that has been cleared. It is a region that gives no indication it ever contained much of anything to begin with. The ring's smooth composition also poses a paradox. Uniform metallicity implies that the gas was thoroughly mixed before star formation began. But homogeneous mixing requires either turbulence or long-duration inflow cycles. Turbulence contradicts the ring's current symmetry. Slow inflow contradicts the ring's synchronized ignition. Neither option fits easily with the chemical reality. The core intensifies this tension. It is too relaxed, too round, too internally consistent to have undergone recent turmoil. Yet something in the galaxy's past must have repositioned or reorganized the gas that later became the ring. The mechanism required to sculpt the ring should have left some disturbance in the core. Instead, the core looks fossilized, untouched. as though it has spent billions of years in a calm gravitational environment. The dark matter halo turns this contradiction into a structural paradox. A halo smooth enough to support a perfect ring should also create a stable disk. But Hoag's object has no disk. A halo quiet enough to preserve the outer hydrogen for billions of years should not simultaneously trigger the collapse needed to form the ring. The same physical potential well appears to both suppress and encourage star formation in different regions. This is not impossible, but it requires fine-tuned conditions that rarely appear in nature without external shaping. The environment makes things more perplexing. The Hoag's object doesn't live in a busy area. It hasn't been hit by close galaxies. There are no signs of tidal forces, cluster winds, or passing satellites having changed its shape. Due to its isolation, evolution should have been easy. Instead, the outcome is so specific that it almost seems like it was chosen. If its peers don't change it, a galaxy should change into either a sphere or a disk. The object that Hoag wrote turned into neither. It changed into something else. The limits of galaxy evolution exposed. Every big problem in astronomy leads to a discussion of the limits of what we know now. Most of the time, these disagreements lead to small improvements over time, like slightly better models, simulations that run more smoothly, and parameter sets with a bit more information. The thing that Hoag's object does is different. It shows a blind spot that is so clear that it calls into question what we thought we knew about how galaxies build structure, rearrange gas, and keep their balance over cosmic time. It shows a part of the parameter space where normal physical processes act in strange ways. This isn't because they break the rules of nature, but because they happen in ways we haven't learned to model yet. The first limit it exposes concerns the interaction between gas and gravitational potential. In standard galaxies, gas responds to halo shape, density waves, or turbulence by forming stars in predictable patterns. Spiral arms collect gas into filaments. Bars drive inflows. Collisions ignite bursts. Hoag's object does none of these. Gas gathered at a specific radius and remained dormant long enough to homogenize before turning into stars, yet the surrounding hydrogen farther out never collapsed. The gravitational potential appears to enforce a boundary where collapse becomes possible only within a narrow orbital range. This suggests that halos, under certain conditions, may impose sharply defined compression zones, something rarely seen in other galaxies. The second limit concerns stability. Most ring structures are transient. They expand, distort, fragment, or fade. Even resonance rings drift over time as bars evolve or disks heat. Hoag's ring appears stable across billions of years, maintaining its symmetry despite lacking the structural supports normally required for such precision. If gravity can maintain long-lived rings in certain halo configurations, then our models underestimate the stability of these configurations or miscalculate how they evolve. Hoag's object implies that extremely stable dynamical states exist, even though they barely appear in simulations. The third limit involves the interplay between kinematics and morphology. Galaxies with spheroidal cores generally lack the rotational profiles needed to host clean rings. Galaxies with rings generally possess disks. Hoag's object breaks this correlation. A pressure-supported core and a rotation-supported ring coexist in equilibrium, sharing the same halo but exhibiting different internal dynamics. This suggests that galaxies can compartmentalize dynamical regimes more effectively than current models predict. The core behaves like a fossilized relic. The ring behaves like the edge of a disk that never formed. The coexistence of these conditions implies that galaxies can develop mixed kinematic identities under rare circumstances. Another limit exposed is chemical evolution. Hoag's ring shows a level of uniformity that contradicts standard expectations for mixed origin gas. Current models assume that gas metallicity always preserves some memory of source material, but Hoag's ring appears chemically smooth despite likely arising from multiple sources or a long reorganization period. This implies that under stable, prolonged mixing conditions, metallicity can homogenize far more effectively than current simulations predict. The chemistry reveals a level of equilibration that should require either unusual timescales or unusually calm dynamical conditions. The most important limit might have to do with how people affect the environment. Galaxy evolution that happens in isolation is usually slow and predictable. Extreme restructuring doesn't happen very often in their frameworks because there is nothing that would make it happen. However, Hoag's object shows that even in the quietest settings, significant structural change can happen. It means that galaxies may change their structure on the inside in ways that aren't caused by mergers, bars, or accretion events. These are internal processes that haven't been added into evolutionary models yet. Hoag's object also hints that rare galaxies may be shaped by slow, cumulative effects, impossible to observe directly but significant over cosmic time. Tiny oscillations in halo shape, minor variations in angular momentum transfer, or subtle gravitational torques could gradually sculpt the galaxy's structure into its current state, without producing obvious disturbances. These processes would be too subtle to leave clear kinematic or morphological evidence, but decisive enough to define long-term outcomes. If such processes exist, they represent gaps in both theoretical modeling and computational resolution. Hoag's object forces one question astronomers can no longer avoid. What else in the universe follows rules we haven't discovered yet? The galaxy that should not exist, yet does. Scientists are learning that Hoag's object is more like a cosmic joke than a real object. It's a lesson that nature is more creative than the models we use to explain it. Every object in the universe that has been studied so far fits somewhere on a range of known evolutionary lines. Ellipticals show the history of mergers, irregulars show chaos, lenticulars show fading spirals, bars show instabilities, and rings show crashes or resonances. None of these are right for Hoag's object. It's in a quiet part of the universe and wasn't shaped by outside forces, but it has a level of organization that suggests either huge amounts of violence or very well-tuned internal dynamics. There is a conflict that won't go away. A structure like this challenges not just the details of galaxy evolution, but the hierarchy of cause and effect. Galaxies form stars based on the physics of collapse and fragmentation, but Hoag's ring collapses at one radius and nowhere else. Galaxies respond to their halos, but Hoag's halo behaves like a perfectly symmetric mold that neither disturbs nor deforms. Galaxies obey the expected relationships between morphology and kinematics. But Hoag's object separates those relationships cleanly, as though different physics governed different components. It behaves like a system assembled in carefully sequenced steps, not one shaped by the chaotic interplay of gravity and gas. The ring raises questions about timing. It ignited billions of years after the core fossilized, yet its metal content suggests a mixture of ancient and intermediate material. The collapse that triggered its formation shows no sign of a strong external impulse, no leftover turbulence, no radial distortions. The star formation history implies stability before ignition, but its symmetry implies that whatever structure governed the collapse acted uniformly around the entire circumference. This is not how gas usually behaves. It clumps. It collapses unevenly. Hoag's gas did neither. The core raises questions about identity. It resembles an early type elliptical, a system typically born from mergers or violent interactions. Yet the galaxy's environment and the state of the surrounding gas argue against a violent past. If the core formed in a denser region and later drifted into isolation, its outer gas would not remain intact. If it formed quietly, its shape would be less perfect and its stellar population more mixed. The core's serenity contradicts every mechanism that might explain how the ring material arrived. The gap raises questions about absence. It is not simply low density, it is vacated, stable, clean. It behaves like a forbidden zone where gravity maintains a structural boundary, something rarely seen in galaxies. If a process cleared the gap, it should have left a disturbance. If the gap never contained gas, the ring's formation becomes harder to explain. Every interpretation contradicts another. The hydrogen superring raises questions about longevity. It stretches far beyond the optical ring, yet it has not collapsed or fragmented. It stores mass that should either form stars or drift inward, but neither has happened. Its stability speaks to long-term equilibrium in a system that should not be in equilibrium if any major event occurred. It is a reservoir that behaves as though time passed without consequence. The symmetry raises questions about probability. Nothing in cosmology suggests that perfect circularity should be favored. Every model predicts imperfections, halo lumps, minor mergers, inflow irregularities. Hoag's object shows no such asymmetry. Its smoothness implies a formation path with improbably consistent conditions maintained over billions of years. The combined structure brings up one last question. Why does every feature that seems to be at odds with each other fit together so well to make one smooth design? Each component, core, gap, ring, halo, environment, and chemistry, supports the others in a way that obfuscates common theories. It's like every part of the galaxy makes up for the flaws in another model, so no path is right and all paths are unfinished. Hoag's object is a great example of how to be respectful about the universe. It's not a bug or something strange that should be ignored until simulations catch up. It shows how to build a formation path that hasn't been mapped yet. It's what happens when the universe takes advantage of conditions that are so rare, well-balanced and subtle that they create a structure that doesn't fit into any of the usual categories, but still makes sense based on physics. It proves that galaxy evolution has secret branches, branch events that are so quiet and uncommon that their offspring are rarely seen. The galaxy should not exist. Every rule says it shouldn't, yet it does, patiently orbiting in isolation, indifferent to the contradictions it presents. It is a reminder that astronomy is not merely the study of what is common, but also what is possible. The uncomfortable implications for cosmic structure. Astronomers are forced to face what Hoag's object's presence means for the universe as a whole, which is a rare and unsettling place to be. Exotic galaxies usually help us understand things better by adding to well-known groups. They change meanings, but never cut them off. What Hoag's object does is more disturbing. This means that our models of how structures are made might not be full because they are wrong, but because they miss rare, highly tuned pathways that only work in very specific situations. The effects reach beyond one galaxy. At its core, the galaxy suggests that symmetry in cosmic structures can emerge from processes far more delicate and stable than anything currently represented in simulations. Such processes would require halos shaped by smooth, uninterrupted accretion flows, or by early universe conditions that favored near-perfect gravitational wells. This hints at the possibility that certain halos formed in environments shielded from the usual chaos of cosmic structure formation, allowing them to maintain spherical precision while baryonic matter evolved inside them. These halos would not defy physics. They would simply reflect a branch of cosmic evolution rarely sampled in large-scale surveys. Hoag's object also hints that internal dynamical processes might be more capable of long-term equilibrium than previously believed. The galaxy's gap, ring, and outer hydrogen envelope behave as though governed by a self-regulating mechanism that sustains structural boundaries across billions of years. If such internal regulation exists, it would mean galaxies can undergo quiet restructuring without visible external triggers. Subtle oscillations in halo potentials, tiny variations in angular momentum transfer, or long-term gravitational harmonics could reorganize galaxies gently and silently. These mechanisms remain below the resolution of most simulations, which rely on approximations that may overlook the kind of fine-grained dynamics required to sculpt a system like Hoag's object. Another implication lies in the limits of observational classification. The Hubble sequence is based on morphology shaped by common evolutionary pathways. Hoag's object resides outside that sequence without violating physical laws, suggesting that the morphological continuum may hide rare attractor states in galactic evolution. In such states, a combination of isolation, stability, and finely balanced mass distribution produces structures that resist typical classification schemes. If galaxies can occupy such states, the taxonomy of cosmic structure must expand. The galaxy also challenges assumptions about the universality of feedback processes. In most galaxies, stellar feedback, black hole activity, and environmental impacts influence star formation and gas distribution. Hoag's object appears to have sidestepped or minimized these processes. Its hydrogen reservoir remained intact without fragmenting. Its ring formed without explosive bursts. Its core settled without repeated stirring. This suggests that certain galaxies may evolve under conditions where feedback plays a minimal role or is suppressed automatically by environmental or halo characteristics. Such cases would be rare, but their existence expands the range of possible galactic life cycles. Cosmologists also must confront the statistical reality implied by Hoag's object. Even if its formation represents a sequence of improbable events, the universe is vast enough that improbable events should occur. The challenge is that Hoag's object is not merely improbable. It sits at the intersection of multiple improbable characteristics. This pushes the galaxy into a category where its existence is not just rare, but qualitatively distinct. It hints that the universe may contain structures produced by pathways so fine-tuned that they appear only once in tens of millions of galaxies. Such pathways would be nearly invisible in broad surveys, but crucial for testing the limits of astrophysical theory. In the bigger picture of how the universe is put together, Hoag's object shows that the universe might be much more complicated than the statistical means that are used in models. Because they show the most likely results of random events, most galaxies follow well-known patterns. Hoag's object shows how rich the cosmic phase space is by showing a less likely but still possible result. That means galaxy creation isn't just a tree with branches. It's a huge, multi-dimensional place where most of the branches are empty but can still form galaxies. It's upsetting to think that if one galaxy exists outside of all known rules, then other galaxies may also live outside of other galaxies. Hoag's object doesn't break down theory, it just shows how weak it is. It makes you think about what is possible, instead of what is typical. And in science, the first step to finding hidden rules is often to think about what might be possible. If Hoag's object represents a hidden evolutionary branch, what exactly started that branch in the first place? The case that keeps scientists awake. There are a few things that all astronomers think about long after the telescope is turned off. It takes time and new information to solve some riddles. Others are still stubborn but easy to deal with, allowing small steps forward. Hoag's object is in a third group, enigmas that can't be solved even after decades of observation, modeling, and theoretical research. This is the case that comes up again and again in talks and on conference slides, and it follows us around the edges of cosmic structure theory. Researchers can't sleep because every time they try to explain it, they come to the same disturbing conclusion. This galaxy shouldn't look like this, but it does. Part of what makes the case so persistent is that the mystery is not encoded in a single feature, but in the seamless coexistence of many. The perfect outer ring alone would be notable, but not alarming. The empty gap would be unusual, but not impossible. The fossil core would be conventional. The hydrogen superring would raise questions. The halo symmetry would be puzzling. The isolation would complicate interpretation. But when all these traits appear together in one system, the mystery multiplies exponentially. This coherence of contradictions is what makes Hoag's object so difficult to ignore. It is not a galaxy composed of strange parts. It is a galaxy composed of ordinary parts arranged in an extraordinary way. Astronomers often revisit the earliest observations made when Hoag's object was first discovered. Arthur Hoag himself initially suspected a gravitational lensing effect, a foreground galaxy magnifying a distant background ring. That interpretation was ruled out quickly, but the instinct is telling. The galaxy looks like two separate systems accidentally aligned, not like a single entity. Even decades later, the impression remains. Hoag's object looks like a composite. Yet every spectral measurement insists it is not a composite at all. The ring and core share the same redshift, the same gravitational dynamics, the same potential well. They are one system, misbehaving as though they were two. It gets more frustrating when you look at Hoag's object next to other ring galaxies. Thanks to big studies and deep imaging, scientists have now made a list of dozens of them. There are twisted cores, tidal tails, asymmetric rings, or attached disks on each one that show where it came from. Hoag's object doesn't carry any. It's the only ring galaxy where the structure looks like it was planned, not just thrown together. That deliberateness is what brings thinkers back to the same question. What conditions lead to accuracy without violence? Even the outer hydrogen ring raises restless speculation. It sits like a reservoir of unspent potential, an enormous structure that should either collapse into stars or disperse. Instead, it remains suspended in equilibrium, as though awaiting instructions. No model captures this level of long-term quiet. Gas is turbulent, gas is fractal, gas collapses or disperses. It doesn't hold its breath for billions of years. The frustration deepens when recalling how often astronomy has faced anomalies that later became mainstream. Dark matter began as an anomaly. Dark energy began as an anomaly. The cosmic microwave background began as an anomaly. Each contradiction forced a leap forward in theory. Hoag's object flirts with becoming another catalyst. Its combination of symmetry, stability, and contradiction hints that galaxy evolution may require a conceptual expansion, not just a technical refinement. But experts aren't sure. Not because the story isn't interesting, but because a lot is at stake. If we agree that Hoag's object shows an unmodeled path, it means that galaxy formation theory, which is one of the most developed areas of astronomy, still has a lot of unexplored land. It means that structure development is more adaptable, varied, and dependent on the situation than what current models show. It means that other galaxies may have similar secrets that are hidden by dust, angle, or distance. This is why Hoag's object keeps resurfacing. It represents the part of the universe that refuses to be simplified. It is a case study in humility, a reminder that even with powerful telescopes, sophisticated physics, and millions of galaxies catalogued, nature still guards pockets of complexity that resist explanation. The puzzle with no missing pieces. A lot of cosmic riddles are like jigsaw puzzles that are missing a few pieces. You make notes, put together what fits, and then look at the parts that are missing, hoping that more information will fill in the blanks. This isn't that kind of puzzle, Hoag's point. The parts of the puzzle fit together perfectly, but the picture doesn't make sense when it's all put together. The observational parts fit together perfectly. The core, the ring, the gap, the halo, the chemistry, the motion, and the environment. However, the final picture doesn't look at all like what we think a galaxy should look like. The paradox is not caused by info that is missing. It is made up of data that fits together too well and suggests a past that can't be true. The most bewildering part is how self-consistent the galaxy appears. There are no mismatched velocities, no hidden substructures, no clumps masquerading as symmetry. The entire system is dynamically coherent, as though every part evolved with awareness of the others. The core is perfectly centered. The ring is exquisitely circular. The gap is uniformly empty. The hydrogen reservoir wraps around the galaxy like a smooth boundary layer. The dark matter potential supports the structure without warping it. Each feature reinforces the others, creating a chain of dependencies so tight that breaking any one link collapses the entire interpretive framework. This coherence is what sets Hoag's object apart. Typical galaxies contain inconsistencies, misaligned disks, noisy velocity fields, patchy chemical profiles, uneven star formation histories. Even the most symmetrical systems hide imperfections. Hoag's object does not. It behaves like a galaxy that ran a script rather than a galaxy that grew through stochastic processes. Its components reflect constraints that seem too strict for natural formation mechanisms that rely on randomness, mergers, turbulence, and environmental shaping. The absence of contradictions within the data paradoxically creates the contradiction within theory. If the ring were slightly oval, theories could pivot toward a weakly disturbed bar. If the core showed mild rotation, models could invoke a faded disk. If the hydrogen envelope were asymmetric, accretion would become plausible. If the metallicity varied around the ring, patchy collapse would be expected. But none of these imperfection-based pathways are permissible because the galaxy refuses to provide imperfections. This problem of perfection extends to the galaxy's temporal history. The ages of the stars in the core and ring do not contradict each other. They simply refuse to produce a narrative that fits any known evolutionary arc. The ring is neither freshly formed nor ancient, sitting instead in a regime where classical ring formation mechanisms lose their predictive power. The core is unmistakably old, but not old in a way that correlates with the ring's later development. The timeline is not patchy or uncertain. It is simply incompatible with every sequence models can produce. In some ways, the environment itself is part of the puzzle. If Hoag's object was in a crowded cluster, its shape might have been caused by interactions. If it was close to a group of dwarves, it might get the missing dynamical nudges from repeated weak encounters, but it's pretty much by itself and in a place with low gravity, so these arguments don't work. Its isolation isn't just a small feature, it's a problem that blocks dozens of paths. This is the reason why Hoag's object is still a case that can't be written off as a mistake in observation or a natural fluke. Mismatches, errors, and chaos are all caused by mistakes. Asymmetries and scars are caused by flukes. Hoag's object doesn't make either. Everything is neat and tidy where it should be, quiet where it should be, and safe where it should be. If nothing is missing from the data, then something is missing from the theory. The closing argument for a galaxy that rewrites the rules. Once you understand what Hoag's object is all about, you can't avoid the truth. This galaxy is not something that can be tucked away in a corner of astronomy and forgotten about. There are clear challenges to the ideas that help us understand how galaxies form, change, and stay stable over cosmic time. It's not enough to say that Hoag's object is strange, rare, or beautiful as the last point. The reason for this is that Hoag's object shows how inadequate the models that were originally designed to explain galaxies are. At every stage of analysis, the galaxy resists assimilation into the known categories. It does not behave like a collisional ring because it lacks the scars. It does not behave like a resonance ring because it lacks a disk and bar. It does not behave like an accretion ring because it is too symmetric and chemically smooth. It does not behave like a polar ring because the kinematics are aligned. It does not behave like a remnant because the core shows no sign of disturbance. It does not behave like a composite because both components share a gravitational identity. It seems like no matter what path is taken, it all leads to a conflict, because the galaxy works in a way that doesn't allow the known forces that shape galaxy formation to happen. Mergers, bars, inputs, turbulence, feedback, and tidal shaping. The object in Hoag's is not non-physical, it is just tuned. It must have been balanced during every process that made it what it is, so no part of the system went too far or too fast. This is not the kind of situation that models are meant to look into. Sims are great at making chaos, not delicate things. They show crashes instead of balance, turbulence instead of calm, and random growth instead of uniform refinement. The closing argument for Hoag's object is that it demands a new conceptual toolset. It highlights the need for models that do not just track violent events, but track quiet ones, models that treat isolation, symmetry, and long-term stability as active forces in galactic evolution rather than passive defaults. It suggests that galaxies can develop fine-grained internal dynamics that shape their structure without leaving obvious footprints. It points toward evolutionary channels that emerge only under extremely rare combinations of conditions, creating a handful of galaxies that fall outside the statistical norms. It also forces a reconsideration of how dark matter halos influence baryonic structure. Hoag's object suggests that halos with exceptional symmetry may act as sculptors rather than containers, imposing structural boundaries that guide star formation in ways poorly captured by current models. If halos can do this under certain conditions, then the universe may host entire classes of structures shaped by gravitational harmonics rather than by collisions or secular evolution. The galaxy also urges people to be humble in the face of the vastness of the universe. The microwave background, the backward motions of planets, the recession of galaxies, the flatness of rotation curves, and every significant R evolution in cosmology all started with a structure that didn't seem to fit. This includes Hoag's object, but not because it disproves existing theory. Instead, it shows the edges of existing theory. It's a warning that the world doesn't have to make things happen in ways that are easy for people to understand. Hoag's object doesn't break the rules of physics, it gets bigger. It pushes theorists to go beyond what they think is possible in terms of structure creation. This makes room for evolutionary options that may be hidden in plain sight, waiting for the right mix of sensitivity, resolution, and conceptual flexibility to show them. The observatory problem. No one predicted. When a new generation of telescopes comes out, scientists look back at the big strange events of the past in the hopes that improvements in sensitivity, clarity, or wavelength coverage will help them solve long-standing problems. Almost every time this plan works. Uncertainty goes down when tools are sharper. They show any parts that were missing, like secret dust lanes, faint partners, underlying disks, temperature gradients, kinematic noise, and so on. This theory doesn't work for Hoag's object. The galaxy doesn't get better as the power of viewing increases. Instead, it gets more confusing. Today's tools don't fill in the blanks. Instead, they erase possible answers by showing what isn't there. The first wave of confusion came when radio telescopes mapped the surrounding hydrogen. Before these observations, astronomers assumed the outer regions must be chaotic, full of debris or wisps from a long-ago merger. Instead, the data revealed a smooth superring of hydrogen, extending far beyond the optical ring itself, free of the irregularities expected from any violent encounter. Rather than revealing a hidden cause, the new data removed the leading explanation entirely. Then came high-resolution spectroscopy. Early hopes centered on the idea that subtle kinematic irregularities, micro-distortions in rotational velocity, slight asymmetries in stellar dispersion, would betray the galaxy's past. But the spectral lines were so clean, so consistent, so perfectly matched across the ring, that they undermined the case for turbulence or past disruption. Spectra often reveal complexity hidden from visual inspection. Here, they make the galaxy seem even more unnaturally organized. Infrared observations too were expected to help. If a faint inner disk existed, too dim or dust-obscured for optical detection, infrared could find the underlying structure. But Hoag's inner region stayed as smooth and featureless in infrared as in visible light. No inner dust lanes, no remnant arms, no trace of the structures that define nearly every galaxy with a ring. It was as if the galaxy had scrubbed itself clean. Polarimetric data followed, probing for magnetic structure. If the ring formed through a large-scale shock, polarized light might betray the presence of aligned dust grains or magnetic shearing. But the polarization signature of Hoag's object is almost non-existent. The dust that typically reveals past trauma appears to be absent or too diffuse to detect. Without magnetic signatures, the list of transformative events that could have shaped the ring shrinks even further. Deep field imaging, which was meant to find star streams, also didn't find any. Stellar streams are the marks of exchanges between galaxies. They are the remaining threads of broken satellites or passing friends. Hoag's object doesn't show any streams that can be found. It appears that the environment around it is unidentified, too quiet and empty. This doesn't make sense for any galaxy with a ring, since rings almost always come with some kind of gravity messing around. Even studies in the time domain, which look for short-lived events or patterns that change over time, don't find anything useful. A nucleus that is active doesn't change color, no bursting from clouds that are shockingly hot. There is no variation in the ring groups that points to turbulence in youth, The galaxy looks like it's frozen in a very stable state, like it's inside a safe gravity shell. The more instruments push forward, the more they confirm that Hoag's object lacks every conventional indicator of its own formation. It is a galaxy stripped of clues. A galaxy with no debris, no distortions, no lingering chaos, no fingerprints of the forces that shaped it. The problem is not that we lack the resolution to see those clues. The problem is that the clues do not exist. This new information makes us think that Hoag's object may not be hiding its past, but it may not have had the past that scientists think it does. It's possible that it didn't change very much. It could have grown in ways that were too slow or delicate to leave scars. These paths, on the other hand, need order, steadiness, and an unusually clean environment. The observatory method fails at every step. It doesn't peel back layers of noise to show complexity. Instead, it peels back layers of assumption to show only impossible clarity. Hoag's object doesn't make sense the more we look at it. Its contradiction comes from over-definition, not uncertainty. If better observation only enlarges the mystery, what kind of breakthrough will finally resolve it? The galaxy that forces us to ask what we're missing. There comes a time when a scientific puzzle is no longer about the thing itself, but about how far we can see, model, and imagine. That point has been reached by Hoag's object. When you look at this galaxy, it's hard not to feel the quiet pressure of a larger question. What basic rule about how galaxies form have we not yet found? The strange thing doesn't point to a small mistake. If we could find that missing conceptual building block, something so basic, the structure of Hoag's object would no longer be a mystery, but something that had to happen. The galaxy draws a line between what astronomers can observe and what they can interpret. It is not veiled by dust, obstructed by angle, or dimmed by distance. It presents itself with unusual clarity. Everything is visible, but not everything is explainable. This mismatch forces an uncomfortable introspection. Perhaps the reason Hoag's object cannot be reconciled with known pathways is not that the galaxy is extreme, but that the frameworks are incomplete. For decades, galaxy formation theory has leaned heavily on violent processes. Collisions, mergers, bar-driven instabilities, accretion shocks. These dominate the narrative. They are common, energetic, and easy to model numerically. But they may not be the only engines of morphological transformation. Hoag's object suggests that slow, symmetry-driven dynamics could also sculpt galaxies under rare conditions. Such dynamics leave almost no scars. They operate over billions of years. They create structures with eerie smoothness. If such processes exist, they likely occur in halos with exceptional initial conditions. Halos too perfect to arise frequently in the chaos of cosmic structure formation. Another possibility is that baryonic physics in extreme symmetry behaves differently than models assume. Gas flows may become more stable, collapse thresholds may sharpen, star formation may ignite in narrower annuli. Structural boundaries may stabilize in ways that defy the typical turbulence-dominated evolution seen in most galaxies. If this is true, Hoag's object is not a mistake. It is a proof of concept for a regime of physics rarely realized at galactic scales. The galaxy also forces consideration of time in a different way. Typical galaxies reveal their histories through disorder. Dust lanes, shells, tidal tails, warps, asymmetries. They preserve their past. Hoag's object preserves almost nothing. It behaves like a galaxy that stabilized early and remained almost untouched, allowing long-term dynamical processes normally drowned out by cosmic noise to shape its evolution. This would mean that Hoag's object is not a survivor of chaos, but the result of an early and enduring quietude, a cosmic laboratory where rare conditions had time to operate. The possibility that subtle internal modes, not external shocks, created its ring opens the door to new physics of halo gas coupling. Perhaps certain halos generate standing wave patterns that compress gas only at specific radii. Perhaps long-term angular momentum exchange can evacuate inner zones without triggering disturbances. Perhaps the gap is not carved, but naturally emergent. These ideas sound exotic, not because they violate physics, but because they demand conditions so precise that they almost never arise. Hoag's object is the kind of peculiar thing that can lead to arrogance if it's not understood. Its perfection makes people want to find dramatic answers, but the truth is probably more subtle. It's probably not in big events, but in slow processes that we haven't figured out how to model yet. This is why the galaxy is still a quiet warning against theoretical laziness. It shows that even with very good models, the world still has structures that change in ways that no one has thought of, so they can't be simulated. The real challenge is not explaining the ring or the gap or the hydrogen alone. It is explaining how all these pieces fit together under one coherent evolutionary sequence. Hoag's object offers no shortcuts, no partial solutions, no forgiving features that absorb contradictions. It forces a confrontation with the possibility that the space of feasible galaxy structures is broader and stranger than expected. Astronomers often say that the world doesn't have to make sense. The moment that phrase is taken literally is in Hoag's object. It represents a part of parameter space where well-known models don't work, where common stories don't make sense, and where the very term galaxy evolution needs to be expanded. The galaxy that redefines what a mystery is. Some secrets leave you guessing with only part of the answer, and others change what it means to not know. This is the second type of Hoag's object. It's not just not explained, it's not explained in a way that makes every belief astronomers have about galaxies seem like it was planned that way. This structure is put together with just the right amount of comfort to look like it can be put into a category, but also with just the right amount of resistance to avoid being put into any category. It forces scientists to face the nature of scientific wonder itself by reminding them that the world doesn't just surprise them, it sometimes throws them off with something that seems designed to be hard to figure out. This feeling does not come from mysticism or exaggeration. It emerges from the way Hoag's object interacts with knowledge. Every known galaxy fits somewhere on a conceptual map. Merger remnants sit in one region, spirals in another, ellipticals in their established niche, ring galaxies in their well-understood zones. Even the oddballs, like polar rings or collisional spokes, fall within predictable boundaries of behavior. Hoag's object sits at an uncomfortable intersection where multiple categories overlap, but none apply. It carries the ring of a collisional system, the core of an elliptical, the symmetry of a resonance, the stability of an isolated system, and the gas distribution of a slowly accreting one. These traits should not coexist, but they do. This cooperation is what makes the story stand out. The galaxy fights the idea that there is only one way for complicated things to happen. It acts as if no single event has shaped its past. Instead, a group of minor forces, each acting over long periods of time, have come together to form a pattern that doesn't normally happen in nature. There are no obvious phase changes because this merging is so smooth. Something, shocked gas, messed up orbits, or populations that aren't lined up right, should reveal the order of events, but it doesn't. In this picture, the galaxy looks fully formed, as if its parts grew up at the same time, under some unknown limits. There is also the troubling sense that Hoag's object represents a kind of evolutionary patience that astronomy is not used to modeling. Most galaxies reveal their histories through scars, tidal distortions, dust lanes, kinematic folds, fading remnants of past interactions. Hoag's object reveals no scars. Instead, it reveals a structure shaped by processes too slow, too stable, or too uniform to leave marks. This implies that galaxies may be capable of evolving through mechanisms that occur at glacial tempos, guided by gravitational harmonics or delicate angular momentum exchanges that take billions of years to manifest. These mechanisms would be almost invisible during the vast majority of their operation, and recognizable only in their end results that resemble Hoag's object. This pushes astronomers into a new conceptual space where symmetry is not evidence of simplicity, but evidence of hidden complexity. The logic used to decode spirals, bars, and mergers is built around asymmetry, because asymmetry carries information about disturbance. Hoag's object reverses that principle. It is symmetrical to a fault. Every line is smooth, every radius uniform, every structural boundary crisp. Instead of revealing its history, symmetry conceals it. This inversion leaves astronomers staring at a galaxy that tells them nothing about how it became itself, because the usual language of galactic morphology, distortion, scattering, fragmentation, has been entirely erased. The deletion brings up moral issues about drawing conclusions about astrophysics. How can you figure out what a galaxy means when it won't give you the usual hints? What do you do when a timeline is made but doesn't have any verbs? Hoag's object says that the universe might be able to make systems that are so well organized on the inside that you can't read their past. It's like studying a river where all the rocks have been smoothed out into the same size disks. The regularity isn't because nothing happened. It's because things happened in such a way that proof can't be kept. This perspective transforms Hoag's object from a curiosity into a warning. It reveals a blind spot in observational methodology, the assumption that galaxies reveal their past through disorder. Hoag's object shows that order can be deceptive. Order can be the mask of processes operating in regimes where the usual assumptions fail. And if this galaxy can hide its history behind symmetry, others may as well. They could be rare, or they could be unnoticed. Overlooked because their perfection reads as simplicity rather than complexity. The final interpretation: why Hoag's object matters. At the end of every deep dive into science, every heated argument, every failed model, and every confusing discovery, one question stands out. Why does this thing matter? Why should philosophers, watchers, and cosmologists from different generations be interested in a single, quiet galaxy that is all by itself? The answer isn't in its shape, how rare it is, or even how many things it contradicts. What Hoag's object stands for holds the answer. In terms of what astrophysics currently knows about structure, formation, and the quiet accuracy of cosmic evolution, this is the edge of what is known. Hoag's object matters because it exposes the assumptions embedded in cosmological modeling. Models are not built to explore rare pathways. They are calibrated to the most common structures, tuned to reproduce the statistical properties of the universe as a whole. They excel at explaining spirals, ellipticals, and irregulars. They reproduce the outcomes of mergers, accretion, and secular evolution. But they struggle with outliers because outliers live in corners of parameter space rarely sampled by typical initial conditions. Hoag's object is a reminder that the universe is not obligated to fill that parameter space evenly. It can produce structures that lie far from the median, structures that reveal blind spots in theory precisely because they are rare. The galaxy also matters because it embodies the idea that cosmic evolution is richer and more subtle than its loudest events. Mergers draw attention because they are dramatic. Bars attract analysis because they reshape galaxies with visible consequences. Turbulence and shocks carry signatures easy to detect across wavelengths. But Hoag's object hints at a quieter regime where slow internal processes sculpt structure over billions of years without creating visible turbulence. If such regimes exist, they are nearly invisible observationally and almost invisible in simulations. Yet they could be fundamental to understanding a small but important subset of galaxies. What Hoag's object means for dark matter halos is another reason why it's important. The shapes of the halos around galaxies determine how they look. But most halos are messy, have 3 axes, and are scarred from the past of accumulation. Extreme halo symmetry may lead to structural paths that aren't seen anywhere else. This is because Hoag's halo looks remarkably smooth and uniform. If it's true, Hoag's object is more than just an interesting idea. It's proof of a very rare type of halos that has very important implications for how big structures are made. In ways that aren't seen in most galaxies, these halos may change how stars form, how gas collapses, and how orbits fit together. Hoag's object also matters because it challenges classification itself. The taxonomy of galaxies, from Hubble's tuning fork to modern morphological categories, is designed around common outcomes. But classification has always struggled with transition objects, ambiguous shapes, and structures that refuse to fit cleanly into categories. Hoag's object stands as a challenge to the assumption that morphology always reflects history. In this case, morphology conceals history. That inversion forces a reconsideration of how astronomers read the shapes of galaxies and what those shapes truly imply. The galaxy is also important because it makes people think of new ideas. Not only data is needed for scientific growth, but people must also be ready to think of possibilities that models don't yet cover. Scientists who study Hoag's object have to think about new ways for gases to move, new ways for halos to behave, new ways for the inside of things to resonate, and new ways for things to form that happen over longer periods of time than what we can see. It encourages new ideas because it goes against what people expect. It's possible that the most important thing about Hoag's object is that it tells scientists that the universe can still produce conceptual story turns. When study seems to be coming together, when cosmology seems stable, a structure like Hoag's object shows up and says the story isn't over. As a sign of cosmic humility, it shows that even with the biggest telescopes and the smartest models, our knowledge is still only tentative. The universe seen through a single impossible shape. Hoag's object is just one galaxy, a very small dot in a world with many, many more. Still, it works like a lens, but it bends thought instead of light. The world looks different through it, a lot more difficult, with more layers, not as clear-cut as the models that scientists have used for decades. As a reminder, astronomy is more than just the study of what's in the sky. It's also the study of how the universe decides to show what's possible. Most galaxies move in patterns determined by chance. Spirals coil under density waves. Ellipticals form through mergers, and lenticulars fade into quiet disks. Hoag's object, on the other hand, shows something completely different. The quiet certainty of a very unlikely event that still happens. This single improbable shape forces a shift in how the universe is conceptualized. It pushes astronomers to think not only about categories, but about the empty spaces between categories, those uncharted corridors where rare structures may live. In everyday work, theory aligns with what is typical. The bulk behaviors of galaxies guide the equations, the assumptions, the initial conditions of simulations. The outliers end up annotated in footnotes or tucked into exception columns. But Hoag's object refuses that role. It demands attention not as an anomaly, but as a signal. It demonstrates that the universe may hide entire branches of formation pathways that only activate under special environmental conditions, or early universe states that modern telescopes rarely observe directly. There is kindness hidden in this galaxy's stubbornness. The opportunity to broaden the conceptual window is a gift given to astrophysics in the form of a problem. Its symmetry, calm structure, and odd consistency make it seem like galaxy formation might be the result of long-term processes that are carefully balanced and don't look like the dramatic events that researchers usually model. It makes people in the field think about what rare parts of space-time these processes might be most common. It also makes it more likely that Hoag's object is not actually alone, just invisible. Some cousins may be so far away, hidden so deeply in dust, or so faint that no one can find them. There may be strange shapes in the world that can only be seen by people who look at them at the right wavelength, depth, and with a lot of luck. In addition to being a structural enigma, Hoag's object changes the way we think about time in the evolution of galaxies. Cosmological events like bursts, mergers, breakdowns, resonances, and instabilities are used in most models. Instead, Hoag's object could be the result of slow evolution that is so secure and lasts so long that it doesn't leave any signs of having happened. If you look at it this way, the galaxy is a symbol of what time can do when it keeps working without being stopped. Over billions of years, very weak gravity waves could move gas, shape limits, and improve structure. What seems like perfection might be the result of processes that take a very long time and don't get to run very often. This point of view adds a higher level of humility. Maybe the world is full of systems that only work at very long timescales that are too far away for humans to observe. There may be frequencies in the structure of the universe that are too slow to measure and too smooth to pick up, but they are strong enough to shape whole systems. If that's the case, Hoag's object is no longer just a riddle. It's also a lesson in the kind of physics that can only happen when nothing gets in the way. The galaxy also shows a truth about science that can be seen in a metaphor. The universe is not an equation, but a story. Most galaxies have stories that are full of fights, violence, and changes. This book by Hoag is a story of poise. It calls into question the idea that the structure of the universe is naturally chaotic. It says that sometimes peace can be just as artistic as chaos. This is why experts keep coming back to it. It doesn't go against physics, but it does add to what physics might include. This galaxy may be telling us that the universe still holds entire categories of structure evolution waiting to be discovered. What Hoag's object leaves behind. When there is this much of a puzzle, the answer is never just about the thing. It's about the mark it makes on the field, the questions it doesn't answer, and the intellectual room it creates. It's no longer just a science puzzle. Hoag's object has become a sign of the edge, a warning that the universe can still make something that makes us stop and think, even in this day and age of high-resolution telescopes and huge cosmological models. What Hoag's object ultimately leaves behind is a boundary, one that marks where current understanding ends and new understanding must begin. It is a boundary drawn not by absence of data, but by an excess of clarity. The galaxy reveals so much so cleanly that the absence of a plausible formation narrative becomes the core of the mystery. It is a system that refuses to cooperate with the expectations built into modern astrophysics. And by doing so, it exposes the heavy reliance the field has on certain assumptions. That symmetry requires disturbance, that rings require violence, that gaps require clearing, that order requires a past full of visible events. All of this is broken down by Hoag's object. It argues for a view of cosmic evolution that is not random but exact, not loud but quiet, and not strong but tuned. It's a sign that the universe isn't just made up of the loudest things that astronomers can easily model. It's possible that quiet processes, long-term harmonics, and secret flows of angular momentum shape galaxies just as much as mergers and shocks. Hoag's object is proof that these kinds of events are not only possible in theory, but also happen in the universe. Its legacy also extends to the psychology of discovery. Scientists often speak of closing the gap between model and observation, of tightening constraints until theory aligns with reality. Hoag's object moves in the opposite direction. It widens the gap. It demonstrates that observational power can outpace theoretical sophistication. It pushes researchers to admit that some corners of structure formation remain untouched by models because they arise too rarely to influence statistical trends and too delicately to survive in most environments. This rarity is precisely why Hoag's object matters so deeply. It is not a representative galaxy. It is a reminder of possibility. It demonstrates that the universe permits solutions far outside the median. It shows that the cosmic story is not a monotone of repeated patterns, but a symphony with movements so rare they play only once in a cosmic age. The galaxy's greatest gift may be the mindset it encourages. It argues for openness, for curiosity unburdened by expectation, for the willingness to imagine structures and processes not yet encoded in formulas. It asks astronomers to look at the sky, not only with instruments, but with imagination, to recognize that nature is capable of outcomes no simulation has yet dared to propose. The hidden chapter of cosmic evolution. In science, there are times when the world seems to point to a page that hasn't been written yet. The way Hoag's object feels is like one of those moves. It doesn't just act differently within a known framework. It also shows signs of a chapter that hasn't been seen yet, a whole set of evolutionary rules that haven't been found because they work in parts of the universe that are too quiet, too stable, or too rare for standard models to reveal. Astronomers who study Hoag's object have to deal with the unsettling idea that galaxies are formed by a wider range of processes than anyone thought possible, and that the visible universe is just a controlled version of a much bigger cosmic arsenal. When you think about what Hoag's object says about how time and structure relate to each other, this thought gets stronger. Hoag's object is like a long piece of writing where exciting events like mergers, crashes, resonances, and turbulence are used to describe galaxies. It implies that there are evolving modes in the world that value stability over chaos, care over violence, and harmonic balance over random growth. These modes may not be common because they are illegal, but because they need a certain amount of cosmic peace that isn't always present. At the right time, in the right environment, inside a sphere with the right structure, a galaxy must form. It must then be left alone for a long time, so that slow-moving forces can shape it. It is such a precise genetic path that even small changes would wipe it out before it starts. So, Hoag's object is proof that the world did set up the right conditions at least once. If such hidden pathways exist, they likely operate below the resolution of contemporary simulations. They would rely on micro-scale gravitational modes that average out in large models, or on subtle feedback effects that disappear when star formation is treated statistically rather than individually. Perhaps they involve shifts in angular momentum that unfold over hundreds of millions of years, too faint to track directly, but powerful in their cumulative effect. In this view, the core, gap, and ring of Hoag's object are not the residue of a catastrophic event. They are the natural equilibrium points of a system that evolved under extreme gravitational purity. This hidden chapter also forces a revision in how cosmic environments are conceptualized. Most galaxies are shaped by neighbors, even when interactions are gentle. Tidal forces nudge, companions stretch, group dynamics perturb. Hoag's object appears to have lived its life in a context that barely touched it, a context defined by absence rather than presence. This absence is not emptiness, it is constraint. A galaxy growing in such isolation must obey the quiet rules of its own potential well, rather than the noisy rules of external influence. It must negotiate its structure with itself alone. This self-governed evolution could produce equilibrium states rarely seen elsewhere. States like the immaculate ring and empty gap of Hoag's object. When you think about the role of dark matter, the secret part becomes even more interesting. Halos are generally not round because they are made by clumpy growth and buildup. However, a halo with very good sphere symmetry could create radial resonances strong enough to shape gas into narrower nuclei, which would stop collapse in the center but promote it at exact radii. These halos might only form in very specific cosmic conditions. They might have been more common in the early universe, before the big structures developed into the web-like structure we see today. It is not possible for Hoag's object to have a structure if it is inside one of these rare halos. Why is it hard to accept a type of cloud that normal cosmology has not taken into account? The problem is not explaining the galaxy. Another dimension of this hidden chapter lies in the possibility that galaxies may possess slow internal cycles distinct from the rapid episodes astronomers usually track. These cycles might involve oscillations in gas density, slow redistribution of angular momentum, or periodic damping of turbulence. Over cosmic timescales, such cycles could refine gas into configurations that defy the usual expectations of collapse and fragmentation. Perhaps the ring of Hoag's object is the equilibrium point of one such cycle, the final state of a process that took billions of years to converge. It's not that this view claims mystery where none exists. It claims possibility that has been ignored. Rethinking how galaxies change shapes is encouraged if Hoag's object is a hidden part of cosmic evolution. It means that the well-known types of shapes like spirals, ellipses, lenticulars, and rings might only be a small part of a much bigger picture. There may be very rare, finely tuned structures in the universe that don't fit into this continuum because they break it, but because they live on the edges of it. If this hidden chapter exists, what else might be written in it that we have not yet found? The universe that still has secrets to tell. Astronomy often works on the idea that the universe will finally be able to be read. They think that as they get better tools, do more surveys, and run more accurate models, the universe will reveal more and more about how it works. That hope is questioned by Hoag's object. It doesn't mean that we don't know enough. It means that the world is made up of layers, and some of them are still out of reach, not because they are too far away or too faint, but because they reveal ideas we haven't even thought of yet. Scientists can see from this that the sky is more than just a bunch of puzzles that need to be solved. It's like a library with books written in languages that we don't fully understand yet. The most important secret Hoag's object brings up is the idea that cosmic evolution might include ways of organizing things that are so uncommon that they only show up once every billion times. It's not like these modes show up with flashy marks or exciting events. Instead, they whisper among the lines and the silence. They build structures that don't seem to fit with the usual random processes of galaxy growth. There are no accidents in the rings, gaps, or cores, and there is no commotion. These structures show up not because the world broke its own rules, but because the rules have parts that haven't been figured out yet. This possibility changes the way astronomers must approach the cosmos. For decades, the dominant methodology has been retrospective reconstruction. Look at a galaxy, find its scars, and infer its past. But Hoag's object presents no scars. It offers no evidence of turbulence, shock, or fragmentation. It behaves like a system that evolved without breaking itself. This forces a shift in strategy. Instead of searching only for fingerprints, astronomers must also learn to search for absences, to interpret not just the features present, but the features missing. The absence of disturbance is not emptiness, it is information. It means something shaped the galaxy without leaving a trace. And that something might be a domain of cosmic behavior not yet charted. The secret is made even deeper by the galaxy's silence. Most silent galaxies are simple, with flat ellipses, featureless dwarfs, or spread-out spheroids. The object by Hoag is quiet and well organized. It's neat and tidy without being dull. While it is solid, it is not harmless. This makes me think of a kind of cosmic craftsmanship at work. It's not clever design, but natural design that comes from perfectly balanced things that don't usually go together. In this light, the world is not just a collection of things. It is also a set of processes that can produce very precise results when the conditions are right. Hoag's object also forces a confrontation with the limits of simulation. Modern computational astrophysics is vast and powerful, but it is grounded in approximations necessary for managing scale. Gas is treated statistically, turbulence is averaged, feedback is parameterized. Dark matter is modeled with simplified interaction laws. These shortcuts are sufficient for reproducing common structures, but may fail for rare ones. If the universe contains evolutionary pathways that require extremely fine-grained physics, tiny shifts in halo symmetry, slow angular momentum drifts, long-term equilibrium states, then current models will never reveal them. Not because the universe hides them, but because the simulations do. This limitation becomes a philosophical challenge. What does it mean to understand the universe when the most advanced tools can only model the most probable outcomes? Hoag's object suggests that rarity is a frontier in itself, that understanding outliers may be as important as understanding the cosmic majority. Perhaps the next breakthroughs in cosmology will not come from refining models of typical galaxies, but from confronting the ones that defy typology entirely. Hoag's object also makes you more humble. Its presence shows that the universe still has a lot of wonders to offer. The universe is not a problem that has been fixed. Instead, it is a huge place where wonder is not a flaw, but a feature. Now that we have precision cosmology and can measure factors with crazy high accuracy, one galaxy can still say that the picture is missing something. It's a warning not to get comfortable and think that the universe we can see is the same as the universe we can know. Discouragement is not present in this modesty. There is a chance. Hoag's object shows that the universe still has mysteries to be discovered, signs of processes we haven't even thought of yet, and tracks of dynamics that play out in ways that aren't explained by current theory. It makes you curious without any expectations. It makes scientists think of new types of structure, new types of evolution, new ways to understand symmetry, and new ways the universe could be organized. The universe is still speaking. We just haven't learned all the languages it uses. The galaxy that refuses to be ordinary. Once every theory has been put to the test and every inconsistency has been shown, the scientist has to take a step back and just look at the thing as it is. This is what Hoag's object wants. As it stands in the sky, it serves as a warning that not everything has to have a clear ending in order for it to have deep value. If anything, the message is that the galaxy won't fit in. It says the world is not a machine with predictable results, but a blank canvas with many options, some common, some strange, and some so incredibly rare that they only happen once in many millions. Its presence is not a mistake that needs to be fixed. Rather, it shows how complicated things are that we still don't fully understand. The final statement begins with a simple truth. Hoag's object is ordinary in its ingredients and extraordinary in their arrangement. It is made of the same components as any galaxy: stars, gas, dust, dark matter. It follows the same laws of gravity, thermodynamics, and stellar evolution. It lives in a universe governed by the same cosmic web that shapes everything else. But somewhere in its history, the familiar processes arranged themselves differently. They produced symmetry instead of asymmetry, calm instead of chaos, structure without scars. And because of that, the galaxy becomes a testament to the universality and unpredictability of natural law. It demonstrates that physics is not a recipe but a palette, one that can paint spirals and ellipticals as easily as it can paint this perfect ring. In a broader sense, Hoag's object becomes a symbol for how science must continuously adapt. Astronomers often talk about closing gaps in understanding, about refining models until they match the universe with satisfying precision. Hoag's object pushes back against that narrative. It reopens gaps, it widens them, it forces new questions instead of allowing old ones to settle. It illustrates that every theory, no matter how polished, is always provisional, always waiting for the next exception to reveal where it falls short. This galaxy also demonstrates the importance of keeping intellectual space open for the unexpected. In a field dominated by massive sky surveys, cosmological simulations, and statistical modeling, it becomes easy to believe that the cosmos is already mapped out, that anomalies will eventually shrink into patterns. Hoag's object is the counterpoint. It shows that the sky still contains surprises sharp enough to disrupt consensus. It proves that no matter how much data accumulates, there is always room for something that defies the distribution curve. The galaxy also carries a lesson about patience. The universe does not reveal all truths at once. Some mysteries demand time for new instruments to be built, for new theories to mature, for imagination to stretch into shapes capable of accommodating what the universe presents. Hoag's object has now persisted across generations of astronomers, challenging each new era in its own way. There is a real possibility that the true explanation will require future breakthroughs, future telescopes, or future theoretical frameworks. This is not a failure. It is the natural order of scientific progress. Mysteries endure until the world is ready to understand them. If this trip through Hoag's object sparked your interest in the same way it has pushed the limits of modern astronomy, then be sure to subscribe, stay curious, and watch this channel for the next deep dive. The universe isn't done surprising us yet, and the next mystery that lies ahead might be even stranger than this one.